Yeah, can do
Hello, everybody. I'd like to welcome Yoda Toyama, who's going to tell us a little bit about a small implementation of our 7RS scheme.
Thanks so much for your introduction. I'm Yota, and I'm a developer of tax scheme. And in this talk, I'm gonna introduce a new tiny like R7RS small scheme implementation for the tax scheme. So let's go. So as a background, like there is a like a R4RS scheme implementation called Revit scheme. I think there was a talk in this like workshop a few years ago. And it's really small like R4RS implementation. Like as it's like level was only 7 kilobytes in binary. Then yeah, like something interesting about Ruby scheme is that like its virtual machine like aims to be like compact, portable, fast and simple, like at the same time. And like Ruby scheme is composed of like two like components. Like one is like a bytecode compiler from scheme source code to like bytecode, and then they implemented like virtual machines in like many languages, like proving portability, including like assembly, C, JavaScript, Bash. Yeah, that's really interesting. So I was really interested in this project, and so the question is, yeah, can we implement the entire R7RS small like a standard like on this like virtual machine or Revit scheme RVM? The answer is yeah, yes we did. Yes we did. Um, so that's how the like, project of Stack scheme started, and yeah, it's like R7RS more implementation, so it's quite like bigger than like a Revit scheme. But it still aims for the same language design of like Revit scheme, like compact and yeah, portable. There are two use cases for this, and one is like running it inside some other like host programming languages environment as like a scripting language. Other use case is that like you run it as like a standalone interpreter, and it's open source on GitHub. And in terms of the like, differences between the stack scheme and the Revit scheme, they are like a bytecode and coding is quite different, and also the implementation of the eval procedure is also debated quite a bit. So I'm gonna talk about those two topics today. So before going into the like details of the stack scheme, I'm gonna explain the like Revit virtual machine. So Revit virtual machine is like very basic like stack machine. But something interesting about that is that every team on the like virtual machine is actually like, represented as lists. So that includes like code, like bytecode, and also like a runtime values in scheme, and like a virtual machine like states are also lists. Like for example, yeah, call stacks or like a value stacks to calculate something. So this is like a Revit virtual machine like implements kind of adapts kind of like a full normal architecture because you can like manipulate like code and data on the heap memory like in exactly the same way. And like right side is like examples of the like data structures on RVM, and the upper is like string like the root like a pair is just a pair of lengths of the string and pointer to the list of characters, and in the list of characters like it just towards the like, both points. And yeah, like this is so on the like RBM representation of like scheme program is called like a code graph, and it's actually just like a DAG of like pairs. And, and as I mentioned, like it contains both code and data in exactly the like a same structure. And yeah, this contributes to like a simpler implementation of the eval procedure, but I'm gonna talk about it more later. So like a RVM or like a Ruby scheme or stack scheme consists of like two components. Like one is like a compiler and the other one is virtual machine. And yeah, like compiler is just like a compiler of text of like a scheme program to the like a byte sequence. It's something like a bytecode. And the virtual machine like a text like a byte sequence of like a scheme program and then execute it. Like the point is that like inside the compiler and inside the virtual machine in both components we use like a code graph as intermediate representation of the scheme program. So in the compiler, like we compile the text into a code graph or memory, and then like later like we encode it into a byte sequence. Like on the virtual machine, like, we do the opposite thing. We first like decode the like byte sequence into code graph, then execute it. So let's take a look at the like one of the example of the code graph. So this is an example of R7RS small standard. So it doesn't work on Revit scheme. The upper is the library definitions and the lower is main program. And in the like, library, we define a symbol called foo, and then like in the main program, we import like with some prefix, and then we define another like a foo symbol, and then like use it in the like final like, expression. And when you compile this into a code graph, it would like yeah, like how do we encode this code graph and how it's different from the like Revit scheme. So in contrast to like a Revit scheme, like a stack schemes, like code graph encoding is more close to like conceptually more close to like a structured memory snapshot. So you can basically like transfer the exact like memory heap memory state inside compiler into the virtual machine. To do that, like, if the like a code graph is like basic like tree, you can use some like a DFS or something to like do a topological sort. But there are some like merges like those symbols, right? like cache those shared nodes like on during decoding, and yeah, like but like we want to make the like decoding algorithm portable. Like for example, like we implemented the virtual machine in Rust, but at the same time, like we want to also target, for example, embedded devices. So we don't want to use some like a complex data structure from the host language. So this cache table is actually implemented as a list on the like, heap memory of the virtual machine. Like this is a story. This is the kind of trick to keep the like decoding and encoding algorithms portable and also like simple. So by having this like a memory snapshot algorithm, like what we can do is like we can naturally encode like those like shared nodes which appear in the code. For example, like sometimes if instructions have like a continuation for both like them and else bodies, and these are like encoded as shared nodes, and also like we can encode like symbols from different libraries like, without any like, manipulation of the code graph or like a pre-processing of the like code graph. Yeah, another thing is that how we implement like eval procedure. So in Stack scheme, like in Revit scheme, the compiler is actually like a separate library. So when you want to like use like eval like a library, you need eval procedure. You need to attach that into the like a main program and then compile it. Like, when we do that, like in R7, R small implementation, it's gonna be really tedious because we want to also because we need to like maintain both like a macro and library systems in those two like separate implementations of like compilers, and so instead what we do in Stack scheme is that like we use like we reuse like a part of the compiler as a like component of like the eval procedure. So what we do is first extract like a compiler of S expression to the like a code graph as a data, like this variable. And then there is a like an incept function in the compiler, and then like it takes the compiler data and source code, and then it embeds the compiler into the source code. And then when you evaluate the like a compiler variable, you get like a compiler function from the expression to the code graph. And yeah, and then like when you apply the like a compiler function to the source code, you get the final code graph. And then you can like encode the code graph, and then you finally get like a byte sequence, something like a byte code. And it sounds like we have two like big features. One is like a hygienic macro system, and another one is like a library system. So like if you like if you remove the eval procedure from the like standard, like, you can actually like expand macros and libraries completely at like statically compile them. But the eval procedure actually needs those information at runtime. So for example, like macro definitions or initialization code for libraries, and also like what like symbols are exported from each libraries. So to encode and decode like this information, we like we basically exploit the power of the memory snapshot algorithm I just described. So those states are represented as another a DAG of the pairs and then embedded into the photograph, and then after that the memory snapshot algorithm automatically encodes and decodes those compiler state, and then we can extract the restore the compiler state at runtime in the scheme eval library. So we evaluated a stack scheme in two ways. One is compactness, and also another one is computation time. In terms of the compactness, we compare the lines of code and also the binary size of the interpreter. And for reference, we compare the TR7, which is the tiniest R7 small implementation before scheme. And in lines of code, we almost halved the number of lines. And in the binary size, we have almost 3 times more binary size of the interpreter. This is mainly because we implemented most of the logic for those rebel interpreter in scheme itself. Those are represented in the serialized code graph. It's by sequence. So that's why it's so small. TR7 is mostly implemented in C, so that's the biggest difference. So in terms of the computation time, this is a relative computation time of different benchmarks. When you look at the last 3 rows, they are computation heavy benchmarks. When you look at the result, stack scheme is pretty much comparable with existing a traditional implementation of the scheme R7 R small scheme interpreter, including the TR7. But at the same time, compared to the most modern interpreter Gauche, it's still far behind for performance. When you look at the top 2 rows, they are benchmarks of just executing an empty scheme program, and other one is a hello world program. I added those because to evaluate the startup time latency of those interpreters. And when you look at the middle two requirements, marked embedded, they are benchmarks of executing just bytecodes, which is embedded into the host language. In this case, a Rust programming language. So in those cases, we have a really small such startup time latency, even compared to the very modern implementation of the interpreter. So this means that the architecture of the Ruby scheme or stack scheme is very suitable for those use cases of the embedded scripting language. And in terms of the future work, so I said RVM aims to be a compact, simple, fast, and also portable. But what it lacks is security. This is because the nature of the kind of for normal architecture of the Ruby scheme. For example, like you can directly modify the like state of the like a stack using the like very primitive procedures in like stack scheme. To prevent this, like we are planning to add like a type checking for like for those like very primitive procedures. And another thing is that like we implemented like virtual machine only in Rust for now, but to prove actually prove the portability, we are planning to like port the virtual machine into other host languages, like including Go. Yeah, there are some other like small discrepancies between the full implementation of the like R7 RS standard. For example, it doesn't have like a stack scheme doesn't have like a full numeric tower yet, and also it doesn't like implement the like it implements like a Unicode I/O, but it doesn't fully support like Unicode case conversions in like a scheme character library. And that's basically all. Yeah, thank you so much for yeah, developers of the like a release scheme and also like early like reviewers, including William. Thank you so much for listening. On the just using the like the original encoding algorithm, but it didn't scale well. But like its startup latency was too high, so we also added some other like optimizations to just to like make the like encoding faster to like make the like to lower the like startup latencies, even with like a kind of like a very big like a set of the libraries in R7RS small standard.
Oh, thank you very much.
Thanks so much.
Okay. Yeah.
Can you make sure turn off?
How do I get to that? I'm sorry, I'm not like.
Your turn. So you
Oh,
go to
yeah.
display. Does it appear?
Go to display. Click on turn off.
Yeah.
Okay.
I think that's good to follow.
And turn it full. Yeah, sure. Which way is this? Okay. Oops. Wait a second. Yeah, no problem. Ready to go?
Yeah. All right. So I would like to welcome next Matthew Plant, who's going to talk about embedding Scheme into Rust.
Great. Thank you so much. It's great to be in a room with all of the Scheme programmers in the world. Yeah, I could not help myself with that joke. So this talk is about a Scheme implementation I've been working on called Scheme RS, in the paper I described it as Goki Scheme. I have not been able to figure out a proper name for it. I thought I was going to switch over. Things happen. So it's not really just about embedding Scheme in Rust, but also about allowing Rust to be accessible from within Scheme and having this sort of Ouroboros Rust and Scheme thing going on. So first, I'd like to talk about, can I get like a show of hands? Anyone not know what Rust is in this room? Okay, I assume that means that I'll quickly go over it. Rust is a systems programming language that's thread and memory safe. It achieves thread and memory safety through a robust type system, which is basically Hindley-Milner plus type classes, excluding everything that you can't do without a garbage collector. So absent of the use of the unsafe keyword, which allows you to do the nasty pointer stuff, people describe them sometimes as nasal demons, Rust code that compiles is guaranteed to be memory and thread safe. So what is scheme_rs/Goki scheme? In order of how close we are to completing each goal. So it's an implementation of R6RS scheme designed to be fast, correct, and safely embeddable within async Rust. Another aspect of Rust I didn't mention is that it has async programming. I won't really get into it because it's not really a part of this talk. There's a lot of stuff that I could talk about scheme_rs, but for now we're going to eschew that just to talk about this one aspect of it. So in terms of R6RS completion, we're actually largely finished. I mean, there's a lot of functions in R6RS scheme, so there's a lot of work that needs to be done. Currently, I'm working on ports, but we have all the control flow operators you'd expect: call CC, dynamic wind, exception handlers. What else? We have records, we have libraries, full tail call optimizations. All of that cool stuff is in scheme_rs right now. In the future, it's designed to be a modern implementation of Scheme that includes all the bells and whistles you'd expect. I'd say if you reasonably expect it to be an R7RS large, that is what we would want to include in scheme_rs. I think the most obvious one that comes to mind, a feature that comes to mind, is the limited continuations. We would love to have that, and I think the design kind of makes it pretty straightforward to include. Much further in the future, there's always something. We want to be a language with modern programming user interface. So documentation generation, package manager, and a static type system. You could think sort of like typed racket, but probably more similar to something like Colton, if anyone's familiar with that. So I'm partial to Hindley-Milner with type classes because Rust is basically that. All right, so why not use an existing implementation? So I think the most obvious comparison is to Guile, because Guile's designed to be embeddable within C programs. The problem is Guile has this very nifty and amazing feature that allows you to extend it with C code that is written in a direct style. So call with current continuation works over both the C and the scheme call stacks. And that's just not really tenable in Rust, as it can be easily used to violate all types of safety. So I have this example here. There's going to be quite a bit of Rust code. Please do not be scared of it. It's all just window dressing, and I will explain it. So what we do in this example is we allocate. Box new is Rust's form of malloc. We malloc an integer. We call a scheme procedure. After that procedure completes, we increment a value and increment the allocated value, and then we free it. That's what drop does. So this is a problem. Guile has a few ways of dealing with this, but they're all quite explicit. But the problem here is if you capture the continuation in the procedure call and you resume that continuation, you have a dangling pointer. And basically, if you wanted to create Guile bindings for Rust, you would have to have every procedure call be unsafe. And that just is not really quite useful for using Rust. And you can replace this box with maybe like locking a mutex. You lock the mutex, you resume the call, and suddenly you have access to some data that you did not lock or was already unlocked. So hopefully that's convincing of enough of why we need a new implementation for Rust, and the other reason being it's fun. We all love making scheme implementations. So what our goals here for for defining Rust functions and having them be accessible in Scheme and the other way around is any Scheme function, including ones that utilize its continuation in some form, should be definable in Rust. The average case of a function that takes input, calls some other Rust function, returns an output, should be easy to implement. Calling a Scheme function with a continuation barrier should also be easy. Defining a function in Rust, like call CC, should be doable. And so how do we go about doing that? So before we consider how Rust functions can be called in Scheme, let's first consider how we convert Scheme procedures into something that is callable in Rust. And the way we do it is a pretty common method, which is we take our syntax, we parse and expand it to an AST, and then we convert that to a continuation passing style. After that, we use crane lift to just-in-time compile that code into runnable functions. Before, this was LLVM. LLVM turns out to be very slow for JIT compilation. And also the fact of the matter is our CPS IR is not terribly complicated right now. In the future, making it more complicated might see more optimization benefits from LLVM, but right now we don't have a lot of those, so crane lift is the obvious choice. So again, more scary Rust code, but basically this crane lift JIT compilation step creates a function pointer. And the important thing to note here really is that it's a function that takes an argument, a continuation, and returns an application. And that kind of is a pretty common structure for Scheme implementations. This allows you to run a CPS trampoline. And what that effectively is you have these functions that return applications, and applications are functions applied values. So you evaluate the function with the values, and you get another application. You do this in a loop, CPS trampoline, tail calls are optimized. It's all great. But the solution comes from this form that we've compiled our Scheme functions into, and that is we want to make it easy to program in direct style with continuation barriers, but require CPS otherwise from our Rust functions. So what we're going to do is our Rust functions are going to be, you're going to be able to implement them in direct style, but every time you call a procedure, it's going to have a continuation barrier. But you will be able to directly implement Rust functions in a continuation passing style. So the unifying factor between these two styles of functions that you're going to be, or not you, but one will be writing in Rust, is abundance of procedural macros to make it easier to do the former and possible to do the latter. So here's an example of a direct style Rust function that is accessible from Scheme. So at the top, we have a bridge procedural macro. So that's what that hash bridge does. It defines the name of it because Scheme is much more permissive for identifiers than Rust is. It indicates which library to put it in. And beyond that, you have a normal Rust function. It's really just how you would program in Rust. And all of the bells and whistles you would expect are automatically handled for you. So for example, in Rust, it is common to do error handling with the result enum. And the result is either the value on the left or the value on the right. I think in Haskell it's either. What happens if, for example, on this line, if you try to convert one of the values into a number and that fails, this question mark will return early with a condition. And when SchemeRS runs your function, sees that a condition has been returned, it will automatically raise that to the current exception handler. So easy to implement direct style code. If you were to put a procedure call into it like this. Now we have an answer to this call CC conundrum in that we do not provide it with a continuation, so it cannot possibly capture Rust's call stack. So how do we go about implementing the opposite, which is when we want Rust functions to have access to the continuation? So this, again, is a lot of very scary code. I apologize. But basically what this is demonstrating is that you can implement apply, the apply function, in Rust itself. And the way we go about doing that is providing you with a bunch of stuff, including the continuation, the exception handler, and the dynamic wind. Eventually, this might just become something like continuation marks, which is a common way of implementing those two things. And so on the left, you see how you would go about implementing apply. And we still need a macro. It does a little bit of work, but much less than the last one. It still has the result type. So it will raise a condition if you return from that, return early with a condition with an error type. It still requires you the name and the library, and in addition, it requires the arguments named. Eventually, we'd like to get rid of that and have it automatically, take the arguments from this function and just read their names and then put them in there. The naming is important for like debug information. So if you just call apply or don't call apply, you just take apply's identifier, it will give you those arguments so you know how to use it in some sense. So yeah, this means that we have basically two ways of calling Rust code that gets basically conflated into this one function pointer. So when you take a look at a procedure in SchemeRS, the function pointer is a sum type between the bridge pointer and the user pointer that I described earlier in a slide. It can also be a continuation pointer, which is the same as a user pointer, but without a continuation. It's just an implementation detail. But when we see these two different types, we apply these we apply those arguments in basically the same way, and we get this sort of unified stack. And this really emphasizes the goal in SchemeRS to make things correct more than anything else before we make things fast, before we make them fast, really. This allows us to implement basically every function you can imagine in Rust. So callCC is implemented in Rust. With exception handler is implemented in Rust, in part because we also include the exception handler. Dynamic wind also implemented in Rust. All of the records, the procedural layer for records, all of the procedural layer for records is also implemented in Rust. I will not lie, it gets very complicated to program in continuation passing style in Rust. But it allows us to write code correctly, and it allows us to get past this issue of this sort of implicit capturing of the call stack that is done by things like, programming languages like Guile. All right, so the next part I would like to talk about is converting Rust types to scheme records. So not only do we want to be able to take scheme values and convert them into reasonable Rust types, like you would, take a value and expect it to be a number and you get a number, or like an I32, I64, etc. Or you see that a value is a string and you want a Rust string and be able to operate on it as you would in Rust. We also want to be able to convert Rust types into scheme records. So among other things, the impetus for this was to allow us to conveniently create condition values in Rust and have them seamlessly converted to scheme conditions. So if we look back at all these examples, that condition structure is the same one that is present in Scheme. So it can be converted to a value. It's a custom structure that is not present initially within value. It is just an extension of the record type. So a Scheme RS value has like 15 tag values or something, and one of them is record, and that condition struct can automatically be converted into a Scheme RS record. And so how do we do this? This is getting towards like the more complicated stuff. I will not really go over this too much, but the basic idea is that we use dynamic dispatch for this. And this is the trait or the type class that you have to implement in order to properly implement, have a type be presentable in Scheme. The only thing that's required is that RTD that returns the record type descriptor of your type. This extract embedded record function allows you to create the parent-child hierarchy that you would typically, that is possible in Scheme, but if you're doing it in Rust, you might want to, you can't really do, there isn't really inheritance, so you have to embed the parent type directly into your record or your struct or whatever. These next two are pretty obvious. They get the field and set the field of the kth field that you might have. So let's take a look at what the simplest case for this, for example, is the simple condition, which is at the top of the, is it at the top of the condition? I can't remember. But regardless, it's all you have to do for it is specify the record type descriptor. And again, we use procedural macros, that's what RTD is, to make this very easy. So you just specify the name, and then bam, you can take this simple condition and convert it into a Scheme value and have it be accessible in Scheme. You can make this more complicated if you want. This is what the message looks like. This includes embedding a simple condition in the message. So the parent is the GC simple condition, and whenever we request an RTD that a simple condition is a subtype of, we get the parent of it. This is a more complicated example of an RTD description. So in message, the message type, the field message is not typically mutable. In this example, I made it mutable to show you that you can specify whether fields are mutable or not. And there's only one field, so we ignore K. And yeah, that is how we are able to sort of bridge this gap between Rust and Scheme and make both like functions and values accessible from each other. So this wouldn't be any interesting if I didn't have benchmarks, and I unfortunately have very terribly collected benchmarks because I only started collecting them about a week ago and then went on a scramble to optimize SchemeRS as fast as possible to improve these benchmarks as much as possible. But the interesting thing about them is they're not as actually bad as I would expect. They're pretty bad, but not as bad as I would expect. So here's an example. This compares integrate, which is the R6RS example code for integration, run with 10 and 100 steps for SchemeRS and a bunch of other implementations. Scheme at the top is Shea Scheme, so kind of like the shining beacon of how fast Scheme should be. And on the left, when we have 10 rounds, it actually performs not as bad as I would expect it to. on the right, you can't really see it, but it goes up all the way in the right of the chart. It's not like outside the range of like Chibi scheme, but it, you know, what can I say? We're working on it. But basically, this is the theme of SchemeRS, in that as things go longer and as data gets larger, I could talk a lot about the garbage collector and how it's not as great as it should be, but as the larger things get, the speed tends to degrade, but for large things, it tends to perform well, at least okay. So in this next example, this is call CC. This is a benchmark that is, if you've ever gone to the call with continuation Wikipedia page, there's an example called Yin Yang, which basically prints church numerals. It's a pretty good example of just calling call CC a billion times. And again, for 100 iterations of that, SchemeRS does okay. Not as good as some of the more well-tuned implementations, but better than Chibi. For call 1000, I'm suspecting there's a bug somewhere. So anyway, it's correct, it's just doing a lot more work than it's supposed to. And now I would like to show you the most shocking thing here, which is that for calling Fibonacci on the Fibonacci sequence, finding the 100,000th Fibonacci sequence, for some reason SchemeRS is the best. And this completely shocked me. I have no idea how this happened, but yeah, for some reason we did right at this point. And yeah, I think that's it. Does anyone have any questions? Thank you all for coming here. Oh, sorry, someone raised their hands. I don't know what the protocol is here. First talk, everybody, sorry. Thank you.
Hypothesis for why it's more efficient. How did you implement numbers?
Numbers? So numbers are, the numerical tower is basically a sum type of the numerical tower. So they're all behind a reference, because we have two different garbage collected types in Scheme, the GC type and then the built-in Rust arc type, which is a reference counted type that doesn't handle cycles well. So we use that for numbers. It's an enumeration that starts with fixed integers, so I64, and then uses a Rust for big integers, uses a Rust library called Malachite, which is basically a Rust version of GNU MP, very solidly built, quite good. And then for floats, we just have, so far we haven't had any, we haven't implemented big floats. So we just have F64s, and complex numbers are just a pair of F64s, essentially.
So I was just conjecturing that your faster implementation of Fibonacci was because of your faster implementation of numbers and of integers.
It is entirely possible.
Yeah, so that's a conjecture.
Yeah.
I've tested Racket and Scheme over the years.
Yeah.
And suddenly the Racket implementation was beating everyone because they had adopted the efficient implementation of numbers. So maybe look there.
Right, yeah. So I would say, based on my CPSIR, this is not my fault. This is someone else's fault that some dependency I'm using. It's interesting that it does slightly beat out Guile. I would also conjecture that part of this, and based on how my test was run, and how my benchmark is run, is that this includes the cold boot of the interpreter, or the compiler, interpreter, whatever. So I think part of it is that SchemeRS is quite fast at compiling small programs as well.
Mm-hmm. Historically, there was old implementation of MacLisp. Mm-hmm. We're talking old days there. And then the implementer had noticed that people would try the Fibonacci function to
Right.
test, and then when they were reading the Fibonacci fib, they would change it into the linear one, and people said, "Wow, it is so fast!"
Yes, I fortunately do not do that. I fortunately do not do that, but that is a great idea. You had a, yeah. It's a good idea though. I should do that.
Yeah, so this is sort of a related question, I guess. And you might not be ready to answer this yet, but I'm also interested in the performance aspects of it.
Right.
So it does seem like, you know, if the integer implementation could be a big reason why your Fibonacci function does much better.
Right.
Whereas your call-CC implementation might be the reason why you're doing the call-CC example significantly worse.
Right.
And so I was just wondering, like, if you have any sense of where the performance degradation comes from.
So,
and I'm particularly interested in the Rust side of this,
right.
as it happens.
So I think the problem with getting an accurate view of where the call CC is going wrong is part of it is over the last like couple of weeks where I've been measuring and improving this. I've improved it basically like I've reduced the runtime from like from what it was like. It was twice as bad before. So over the course of that, a lot of it was the garbage collector being pretty slow because we can't use a tracing garbage collector. We have to use something called concurrent cycle collection, which I've managed to improve quite a bit, and that could be a whole another talk, I think. It's just going to require a lot of implementation. I think there's a ton of obvious things, like we have, we box basically every procedure, that every continuation gets boxed. The only optimization we do on the CPS side, besides eliminating some boxing from arguments, is like 2 rounds of beta reduction. So there's a large number of things that can improve on the CPS IR. So, and I think that it's a solid foundation to be fast in the future, frankly, but not right now. And that's kind of why I chose it. I didn't choose it because it would be fast immediately. In fact, when I switched to CPS, I didn't have a beta reduction. It blew up everything by 300 times. So it's a very much a work in progress and creating more optimization passes and all those sort of things.
It was a sort of an early stage to ask that question.
Right.
But yeah, I'm still interested.
Yes. So anyway, thank you very much. Thanks to everyone.
All right, thank you very much. Now we have Andre and David, who's going to talk about testing for finite state machines.
Yes. Okay. As you all have heard, my name is David Anthony Fields, and this is Andres Garced, and we'll be talking to you today about automatic invariant testing for finite state machines. This is joint work with Sofia Tarano and Marco Morazan from Seton Hall University. A modern trend in teaching formal languages in automata theory follows a programming-based methodology. One approach to following this trend uses FSM, a domain-specific language embedded in Racket. It allows students to design, implement, validate, and verify the machines that any student may encounter in a typical flat course. Tightly coupled with FSM is a book, problem-based formal languages in automata theory, where students are introduced to the design recipe for state machines. And following this design recipe, students then develop state invariant predicates for each state, and they have to design, implement, and validate these invariant predicates. While designing and implementing these invariant predicates may be straightforward to students, how are they supposed to test them? Should these tests solely rely around the implementation of the invariant predicate? And if you're thinking, yes, I'm sorry, but you're sadly mistaken, because the invariant predicates have to rely on the transition relation that they develop. And by that, I mean they have to test all the paths that lead to the state that they're developing the invariant predicate for. Now, this is an NP problem, and I would like you to consider the following example. Consider the number of possible paths without repeating a state in a complete graph of n nodes. The number of paths of length 2 is n times n minus 1, and the number of paths for length 3 is n times n minus 1 times n minus 2. So we can see that the number of paths for length n would then be n factorial. And if we wanted to find the total number of paths for the entire machine, we'd have to sum up all of these n factorials. So I think we can all agree that asking students to write this many tests is just unreasonable. So today we'll be presenting a tool that automatically tests all invariant predicates by traversing the transition relation that students develop to provide a thorough test suite for their invariant predicates. So before I get into the implementation, we should first highlight how we FSM and how students are then able to program within it. So we'll look at a DFA for the language where all words contain the pattern AABAB, and the design idea for this machine is that each state will contain a different progression of the pattern. For example, the starting state will have none of the pattern being detected, and the final state will have the pattern AABAB be detected. So here we can see the implementation of this DFA, where at the top we have the state documentation. This is where the students would informally define their invariant predicates. In the middle, we have the implementation of the machine itself, where the arguments are as follows: the set of states, the input alphabet, the starting state, the set of final states, and then the transition relation. And in the case of a DFA, this has to be a transition function. And at the bottom, we have the unit test for this machine. For this to be a thorough suite, students must include words that are both in and not in the language. And finally, we have the transition diagram of this machine at the top, where the starting state is highlighted in green, the final state is double circled, and all edges in the transition diagram correlate to one of the transitions found within the relation. So assuming that all of these tests pass, the students can then move on to formalizing their invariant predicates, where they would then take these invariant predicates from the state documentation and then turn them into code. So for the sake of brevity, I'll only show one of them. So we have the invariant predicate for A, and the purpose of this is to determine if the consumed input only ends with a single A and doesn't contain any other prefix of the pattern. So here we have the test for the invariant predicate, and I want to draw your attention to the first line, check invariant holds, as this is the problem that we're going over today, or we're addressing today. So here we have the first test in this suite, A, which tests the edge from S to A, and the second test will test all of the edges highlighted in yellow. So I now have a question for you guys. Do you think this is a thorough test suite for this invariant predicate? Yes, you would be right. The answer is no, as all of these tests, or all of these edges highlighted in blue, are also words that can be correlated and used to test this invariant predicate. So as I've mentioned earlier, to thoroughly test an invariant predicate, we have to rely on the transition relation that the students develop. And for any of you guys curious, the number of tests that the students will have to write for this machine in particular would be 50. So now to circle back to the implementation of our tool, we wanted to find all words that use a transition rule at most k times. So our implementation can be divided into 3 main phases. Phase 1 is the machine refactoring, where we remove all dead states. Phase 2 is the computation generation, where we would accumulate all paths from any accepting computation. And finally, we would then go and test the invariant predicates after using the paths that we then generate. So for phase 1, this one is pretty simple. We just take any states that don't transition to or they don't have a path to a final state. So if we look at this machine here, we can see that this state DS does not lead to any final states. So we can simply just cut it off in all of its transitions without changing the language of the machine, and then we can then take this machine and then move on to phase 2, where we then generate a test suite using the refactored machine by doing a breadth first traversal of the transition relation. So in doing this traversal, we accumulate two values, the queue of computations to explore and the list of computations found. So now I'll run you through a quick example using the machine that we just refactored, where our starting queue is all of the rules that are usable from our starting state. So that would be SBB and SAA. And then we can take the first of the queue, add it to our computations found, and then we can then extend, this rule SBB with another applicable rule, BAB. We can then do the same for SAA, add it to the computations found, and then extend it with ABA. And then in a similar manner, we can do the same process for the remaining two rules. And then now that our queue is empty, which we see here, and we have all of our computations, we can then move on to phase 3, where we then go to the invariant testing. So we take all of these paths and then associate them with their correlated state, and then we test each invariant predicate using the rules that we have here. Now this tool should return a list, and this is a list of pairs. If the invariant holds, then this will return an empty list, and if any of the invariants fail, it will then return a pair where it'll have the state and the corresponding word that the invariant does not hold for.
So now that we've discussed the design and implementation of the tool, we can discuss the practicality of this tool in a flat classroom. So thoroughly testing machines like this is computationally very difficult, and thus we need to determine whether it's actually feasible for students to use this tool in a flat classroom. And if it is, what defaults, for example, the maximum number of times a rule can be applied should be. In order to determine this, we ran an empirical study on the various machines that we collected from different flat textbooks to determine if the tool would be able to run in a feasible amount of time on those machines. There were 17 in total, and you can see the characteristics of these machines on this table here. So we have the number of states, the number of transition rules, and the number of the type of machine, how many transitions are coming in and out of the dead state. And here we can see that these machines are all fairly small, containing 10 or less states, because these were found in introductory flat textbooks. However, some of them are still somewhat complex, containing 20 plus, 30 plus, even 40 transition rules. So in order to determine what the default number of maximum rule applications should be, and also whether or not this tool refactoring the machines was a feasible optimization strategy, we collected the number of rules needed to thoroughly test the machine, and we denoted between whether the machine was refactored and not refactored, and whether we only used a rule at most once or at most twice. And so here we can see that for when the machines actually did have a dead state that could be removed, the number of test cases is reduced significantly. And so it does make sense, it appears that it does make sense to include this optimization for the tool. Another thing to note is that some of these examples are actually infeasible, and when it's denoted as infeasible, it means that the laptop actually ran out of memory. And so because there are so many examples, test cases being generated, because we're starting to hit up against the wall of NP, the laptops just simply do not have enough memory to compute these examples. And thus, it's because of there being so many unfeasible test exam machines for when the maximum number of rule applications is 2, we have decided to set the default to 1. However, we've included a keyword argument so that students are able to increase it at their will. So now that we've determined that it is practical to include these, to use this tool on typical examples found in flat textbooks, we wanted to see what the runtime characteristics would look like. And so we ran an average of, we took the average of 50 experiments across all those machines on the laptop provided to students at our institution, so Lenovo X1 Yoga. And we had 2 of them. One of them was running Windows and the other was running Linux. These are the results for when there was only 1 rule application allowed. And here we can see that for all the machines aside from machine 15, the runtime was under a second. And so we feel that, at least for using the rules at most once, that it is most definitely practical for students to use this tool in the classroom. Interesting to note is that when there are no dead states to be removed while refactoring, the performance hit is quite large, and thus we also made the optimization of refactoring the machines to be a keyword argument, with the default being that it does not, so that way students don't incur this performance hit unless they actually need it. These are the results for when we allowed rules to be used at most twice. And here we can see some of these unfeasible examples popping up again. And what's interesting to note is that there's some examples that will run on Linux, as we can see here, but however, will often run out of memory on Windows. And one reason we suspect this might be the case is that the out-of-memory killer is killing processes on Linux, which is something we actually observed occurring on the laptop, and thus was making more memory for use for the tool that wasn't occurring on Windows. Now that we've talked about the tool, we can actually see it being run. So here we have a student-submitted design for the DFA that we looked at previously. And if we look at the transition diagram, the keen eye among you might notice that this contains a bug and is different from the one you saw on the slides previously. So if we test it using a variety of different invariants, oh goodness. We can see that there are two invariants that do not hold, the invariance for S and the invariant for A. And so if we take the word that breaks the invariant for A at the bottom and run that in a dynamic visualization for the execution of the machine, we continue stepping through, we can see that the machine rejects when the transition is coming out of D. And so if we look at the state documentation for this machine, we can see that the largest prefix in this case is AA, and thus shouldn't actually be going to A, but rather should be going to B. And thus perhaps the student made a typo somewhere along the way. And if we actually fix that mistake such that it follows the state documentation that the student wrote before, we can see that now all the invariants hold. So now that we've talked about the tool that we've implemented, let's talk about how some other people have implemented tools to test machines. So JFlap and Automata Tutor, Automata Simulator are tools that allow students to implement machines and test them. However, in contrast to FSM, they do not provide support for testing invariants. Automata Tutor is another tool that provides predefined problems for students to solve. In contrast to FSM, that doesn't allow for the definition of arbitrary machines, and it also doesn't provide support for testing invariants. Proof Checker is yet another tool that allows students to test machines and does provide support for testing invariants. However, the way that it does so is by the generation of random words, and thus doesn't provide nearly as thorough test coverage as a tool being presented today does. To conclude, today we have presented a novel tool to test invariants in machines via the use of traversing all possible transitions, and does so by single expression, and allows the programmer to debug their design and have much more confidence in the design before they actually attempt to verify it. For future work, we would like to use this software as the basis to start generating test cases using Quick Check for those examples in which it's unfeasible to use this tool. We'd also like to extend this to work with pushdown automata, and we'd like to determine the effectiveness through the use of human factor studies.
Thank you very much. Any questions?
Thanks for the talk. Is there a specific reason why you chose like a testing approach over like a full-fledged verification approach? Because for finite state machines, it should be doable in principle.
I think it's mostly for the ease of proof. So we find that the actual proof, proving that the logical equivalence between the language of the machine you've designed and the language that you're designing for is much easier to write if you do it through the use of invariants. And so I guess it's more just an ease of difficulty.
Yeah, I guess I have a related question, which is, what is the actual expressiveness that you need from those invariant predicates? Right, so it looked like you had kind of arbitrary functions as the predicates, but it could be the case that if you didn't really need them to be arbitrary predicates, you could express them in a DSL, then verification could potentially be much more practical.
I could see that being the case. It could be something that we could look into in the future for sure.
Sorry, I want to repeat the first question because I didn't really understand the answer, right? Like, these are all highly decidable systems. So you could still have people write the property-based testing predicates, but you can actually just test the predicates directly. You can just, these are decidable. Like, why do you need to do any unit testing at all? Those are not, it felt like your answer was you wanted people to be able to write the properties, which is fine, but you still don't have to test it using property-based testing. I think that was your question, yeah.
So
everything here is brutally decidable.
Yes. I mean, I think part of it is that this is one of the first times, aside from an introductory like discrete mathematics course, that the students at our institution are getting into like verifying programs, and thus it's easier for us to transition them into verifying things when we can kind of transition them through the use of invariant predicates. I think perhaps if we had more experience, if the students had more experience in actually verifying programs in that way, that maybe we would be able to do it like that, yes.
Okay, my follow-up, a separate question is, you said you wanted to do user studies. I want to know what the user studies are. What do you want to study?
I think some of the research questions we'd like to examine in the user studies would probably be whether the students felt that it was helping them in debugging their designs, if they felt that it was straightforward to use, and if I think those would be the two main points really. If they felt that it was straightforward to use, if there was any, I guess, like UX issues with the interface of them actually using it, and if it felt it was actually helpful for them to actually like have more confidence before they go and verify their design.
Thank you very much.
Yeah. Start presentation. Nope. Let's see, which one do I want to do? This one? Nope. Let's try one. Restart the state. Uh-huh. Oh, I know what's happening. Yeah, it's just my display is set to mirror instead of extend, and it's automatically changing. So let's set it here. Where is it? Now there we go. Stop mirroring. Okay. Now that it's stopped mirroring. I'm gonna have to do it from here. No. Yeah, that's what I'm doing now. It's you said this is abort. There we go. Then should I click this button? There we go.
All right, so now we have Jan Paul, who's going to be talking to us about typing in Scheme.
Okay, so hi, I am Jen Paul. You probably have seen me doing AV here, and I just failed at doing AV for myself, so that's fun. But I actually do research, believe it or not. So I'm going to be showing something I worked on during the summer. So as a quick caveat here, before this I didn't really do any racket or scheme. This actually just came as a side effect of another project I was working on, which I'll touch on a bit, but since it's out of scope, I won't really go into it unless people have questions about it. So yeah, as this being more of a position paper, I want to know exactly how this community feels about this sort of default type setting I've been working on. So let's get started. Okay, so we can start with an example. And the idea here is that we want to be able to identify from the programmer's perspective what they believe is going to happen in their code versus the probability of something happening in their code in a quantitative sense. So we have this example here. So this is a load balancer. Normally here, we're given a latency measurement from a service instance, and then it's going to compute a composite health score by combining the average latency with the failure rate, what's happening there at the top. So here, we're using trimmed to ignore outliers. So this means that it's going to drop the top and bottom 5% of measurements to avoid any skews on occasional spikes or timeouts. So what happens here is that service instances collect buckets of the timing data, and you have certain beliefs about these buckets. So under normal operations, we can have hundreds of samples per bucket, and alpha is a tuning parameter. So in this case, if alpha is 0, we only care about latency, whereas if alpha is 1, then we only care about the failures. And then the monitoring ensures that the buckets are never empty. So the obvious issue here is that edge cases can exist. So small buckets during startup, you can also have misconfigured alpha values. And this trimming step here is going to be the tricky part to try and get a sense of what we believe about it. So if we take a sorted list and drop k elements from each end, and then compute the mean, then this can fail if the list is empty, for example. So this is a basic check you want to make. So this is a mental model that the programmer has before we even start to think about the objective nature of the list, that it shouldn't be empty. By that I mean a programmer might think, okay, we have 100 plus samples, so trimming is safe in a quantitative sense. We rarely get small buckets and need guards. And the buckets should never be empty because of monitoring, because monitoring ensures collection. So what we want to be able to do here is give some flexibility to the type system to encode these 3 different beliefs that I've described. So instead of just saying, okay, there's going to be a binary of this will work or this will not work, statically speaking, we want to be able to express a very kind of hand-wavy notion at first of this usually works, or this is an edge case I don't want to optimize for.
without having to add expensive runtime checks everywhere. So yeah, these are some traditional approaches. And so the trade-offs here aren't necessarily bad. I wrote bad there, but they're not necessarily bad trade-offs. They're just trade-offs that you wouldn't really want to deal with in this specific mindset. So you don't want to add runtime overhead, and annotation burden kind of would defeat the point here, although ideally this would be the most formal case. We're dealing with programs and beliefs that are very simple and compositional in nature, in that you don't really want to spend so much extra time developing on this meta annotation language. So we want to try and simplify it as much as possible while maintaining some static guarantee. So, oh yeah, and then ideally then optimize the generated code for this common case. So what does this look like then? These are the possibility rank types. So these are completely annotated by the programmer. And in this case, for this example, I've annotated a couple of them you can see. So rank 0 is going to be the normal case, in which you have a list of length greater than 20, and in which alpha exists in the normal domain you'd expect it to. But then here, and you can see this here, you can see my mouse. Yeah, you can see this here in the assume default. What's happening here is that the programmer is actively, explicitly annotating what properties are going to assume to hold in the cases. So here, there's nothing being checked at runtime. This is completely relaxing the type system in a way that we are literally trusting the programmer's intent for what they believe to be an unusual case or an exceptional case. And then what you should annotate as a type error, which is the case here, rank infinity. So this is going to be a rank that you can never possibly reach. Ranks in which everything will definitely fail. So type checking will definitely fail if n equals 0 in this case. So how do these cases actually get implemented? I'll skip through that for a second here. Okay. So this is the policy table. And so this P table is going to be working with the typing rules that are implemented. This is in, if I go back here, that this is the overall architecture of everything. So you have the rules in turnstile. And so you have these, this assumption rule that's going to work in tandem with the subsume of the policy table for these operations. And this is what's defined on a program case-by-case basis for the for that particular program or for that particular program. So assume default introduces plausibility assumptions. So this is the keyword here on plausibility. So yeah, we extend the environment with variables at rank 0, the normal case, and these have now been formally declared as a normal operation. In the primitive rule, we check all arguments and get their ranks, and then we look up the operation's base rank from the policy table pi, and then the result rank is the maximum. So it's going to be the weakest link principle here. So that means that if any sub-expression needs exceptional assumptions, the whole expression does. And then this works as kind of a safety chain here. And so the policy table here is going to be very domain specific to whatever you're operating in. And then this just serves as a map. So you can think of in division in general can have rank 1, that means that it might be 0, but it's unusual. It still needs handling, something of the sort. So if I can go back here, hopefully that clarifies a bit how much trust we're putting on the annotations to try and just weaken type checking and just get your program running. So this might seem a bit bizarre at first, but then what I mentioned at the beginning of how I came to this kind of path here is that this works as a way to introduce a gradual probability. And by that, what I mean is, I won't go into it super in depth here, but I have an actual refinement here via an abstract interpretation that essentially gives me the tooling necessary for whenever a programmer writes these qualitative beliefs that they've specified. Again, this is very just trusting the person programming. Whenever you get actual quantitative information, so this can be later on, so you can say in an example in which you would need to know what percent a certain package might have, what percent of dropping a certain package might have in a network or something like that. You might not have this information immediately, but you can write a qualitative belief about it. And so the idea here is that we create these partial orderings, which I'm not going to go into exactly here, but once you have these orderings, which are defined in the assumed default, then once you discover these probabilities in whatever way, you can actually gradually replace the qualitative notion with an actual formal guarantee of a probabilistic guarantee. And if the probabilistic guarantee doesn't hold, like if you said that an event A is at least as plausible as an event B, but then the actual numbers you got don't match that, then that's actually going to fail. So this is the main domain in which this sense of relaxing the type system, I believe, makes sense. And so we can now go real quick to the constraint solving and error reporting. So this is now going back more a bit into the relevant to Racket here. So for the constraint generation, so for each operation, we generate some inequalities. So when we see the vision, we look up in the policy table and we see what has been defined, and then we generate some constraints. So then the result rank is at least as bad as its dependencies. Then we have a lexicographic minimization using priority ordering. So then we first reject any rank infinity, so any type errors, and then we minimize to the maximum rank. So in our previous example, it would be rank 2, and then we go to rank 1, and then finally rank 0. So then the idea here is that we want to encode, we want to be able to encode this with the exponential weights, so that we know that a rank 2 actually outweighs a rank 1 meaningfully. So then, yeah, this is the tooling that ensures us to find the most plausible typing, not just a valid typing. And then finally, we have error reporting. So then, this is like the most concrete thing you can get out of this, in this, at least in Racket, I believe, is that you can get some relatively nice errors, I think. So then when you have a constraint failing at rank 0, then we just trace back and we can, D3 constructs the counterexamples showing the concrete inputs that violate them, and then, yeah, we get the, which assumptions were actually too optimistic, concretely. Yeah, so then this is the safe execution. So this is what it looks like in practice for what I had shown previously. And yeah, the idea here is that the compilation overhead is minimal. So yeah, here we go. And then, so this is a quick why this matters table here. So just trying to understand where this fits in the context of all other approaches here. So the idea really here is to try to annotate beliefs without having to examine actual information at runtime, and then give a gradual path to be able to formalize these qualitative beliefs quantitatively. And then racket and turnstile here are pretty nice because I can just do this via macros. So I don't have to implement a whole separate interpreter for this. So there are some limitations here. So the current limitations on this are for module boundaries and higher order functions don't really work. So this doesn't work modularly yet because I'm not really sure how to get that working. But yeah, so here are the next steps. So yeah, what we want then is to be able to get this good enough typing system working. And then there's two possible directions: either look more in this racket domain and try and make actual usable programs, or also trying to go into any other any other domain in which qualitative information would be useful, and you would want to replace it with quantitative information at the end. And yeah, generate optimized code that works on whatever the programmer believes. And yep, that is it. Yep.
Thank you very much. I think we have a question in front and then back.
Okay, thanks. This is interesting. My sort of thinking about this is, could this be used in other languages for something like function specialization, like saying, okay, well, this is the common case. 0, 1, and 2, the parameters 0, 1, and 2 for this function are the common case. So to sort of give a hint to the compiler that, yeah, we need function specialization for those cases. Just like just-in-time compilers sometimes do that. This is a common case. Let's aggressively optimize for that. Would that be a thing that this could be used for?
Yeah, that would actually be. Yeah, that'd be pretty good. So I gave again the idea here is also trying to get ideas as to what domain this could be useful in. I gave this talk about a week and a half ago, and somebody suggested this as well. Yeah, this seems good. I haven't done any technical work to try and explore this more, but yeah.
And usually we don't, compiler writers usually don't trust the programmer, which is sort of
I love this work. I'm actually not convinced that what you're doing is a form of gradual typing, because I think the way I would play it,
I'm not convinced either, to be fair. I'm not convinced either, to be fair.
yeah, well, because the way I see it is what you're really doing is you're relaxing what the progress theory means. So we did an honorable paper 10 years ago on what we call progressive types, which is basically the idea. I view this as like a really nice generalization of progressive types. In our case, we just did it across the board, so we didn't have to worry about the modularity problem because you were just producing what the progress theory gave you on all modules across the code base. Your problem is you're trying to do this at a more fine-grained level, and so you have to worry about module boundaries and stuff like that. But it's really about progressive weakening rather than about, and in fact, it's funny because your paper has this type racket example. I think like everybody who runs into type racket is inspired to write papers because it's like, how do you make anything work here, right? It's just so clever and complicated that numbers and type racket. So I'm just curious if that resonates with you, or whether that's at all a reasonable way to think about this.
I mean, yeah, it definitely does. So this is kind of a Frankenstein of a project in terms of the motivation for it, to be fair. So initially, the core motivation for this is to be able to solve. So this is what I didn't get into for the sake of scope, but it's to be able to solve. How do I say this? Probabilistic paradoxes. That's like the super specific domain. So this can immediately counter like the lottery paradox So just super, super quick, in the lottery paradox, so you have a lottery where there's 100 tickets, and then you can have an assumption that any ticket has a 99% chance of being the losing ticket, but if you follow that conjunctive belief, at the end, you believe that every single ticket is going to be the failing ticket. And so this domain can let you encode that problem with partial ordering to fix that. And then, so because of that motivation, I think that that general like philosophical thought is like a general, like you said, not an issue, but like a problem you encounter a lot in typing in general. And now I'm trying to pull that down.
Any other questions? All right, let's thank the speakers again.
All right, hopefully I don't mess up anybody else's AV.
mean, no, I just meant it wasn't like a lapel mic or something. It's just a handheld. Okay, perfect. I mean, I guess I figured, yeah.
Hello. 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 I think it works.
All right, thank you very much. So I'm here to tell you one weird trick about macros in bracket and scheme. All right, and so as mostly just a running example, I'll use continuation passing style translation because hopefully this is something you're at least somewhat familiar with, so you don't have to worry too much about why we're transforming or what we're transforming, but essentially how the transformation works. And so here is the kind of base, just continuation passing style translation. Very, very classic one. If you've seen it before, you've probably seen this one. If you haven't, you don't really have to understand what that code does. We're just trying to turn the left-hand side into the right-hand side, right? And so a great thing about Scheme and Racket and other languages with similar macro systems is that this is not just a theoretical tool, but actually executable program, right? So here is that exact same transformation written as actual code that, I mean, most of this I actually tested in Racket, but I mean, it's just as well in Scheme. It is the CPS transformation, and there's 3 steps, and the first one is what happens when you see a lambda. So the actual lambda symbol, let me see and make sure I'm in front of the mic. Yes, the lambda symbol is going to be kind of a special identifier we look out for, right? That's the first thing in the parentheses of the syntax rules. And so we say, okay, if I CPS a lambda, I see there's a parameter and a body, so then we rewrite it according to that specification we had from before. We're going to take a continuation and then return a lambda, or we're going to apply that continuation to a lambda with the transform body. If I see a single function applied to a single argument, we transform it. And in the last case, I hope it's an identifier because nothing here actually checks for it, but we're just going to assume that it is. And then we take the continuation, pass the identifier to the continuation. So this is fine, this works, and then you can write code and use it, right? So we can say define some example program and say it's going to be the CPS of this code, and it will do the CPS for us. So you can like play around with it for real, and then you can pass in an initial continuation and some parameters for f and x and get it to work, and you'll get the right results. But then if you actually peek under the covers at the expansion, it's not a pretty sight. And why not? What's the big problem is there's these reductions everywhere. So I've got a lambda k blah, blah, blah applied to a lambda f1 blah, blah, blah. And that's like a step that I should have gotten rid of, right? It's kind of in the way. It's not really relevant to the original program. It's this extra step. It's an administrative step. And ideally, we can get rid of that. And in fact, there are tricks to get rid of that. But what's the problem? I mean, okay, so maybe this is slower, right? If our scheme implementation is not smart enough, it may not get rid of these extra steps, so that might take extra time at runtime, and this is going to depend on your host implementation, how slow or fast this is. But that's not really my motivation, at least when I started thinking about this. It's just the fact that the output of macro expansion becomes very quickly completely impossible to read. And this matters a lot when you start writing your own macros that are doing these kinds of transformations. And if they're very higher order, it's hard to interact with them at the REPL because pretty much everything you see is either procedure or error, which is not very useful feedback if things are getting transformed into weird ways. And then the last resort is you open the macro expander and you say, what does it go into? And it turns into a mess. And then I have no idea what's going on. So just as a way to keep my own sanity while working on macros, I needed to have a more clean output just to see and tell what's going on. So, okay, what can we do about this? So there's actually a lot of literature about this on CPS in particular. That's why I used it as a running example, because this is a very well-studied problem. There are different techniques to get rid of administrative reductions sort of in advance to running the program. Here I'm focusing in particular on the ones that try to avoid creating the administrative reductions while the expansion happens, so like we won't output them in the code in the first place. And so here is a variant on CPS which does not produce the same administrative reductions, and why not? So we could actually get a redx in our output program, but that's because the programmer may have given us a redx. So if they say lambda x applied to something, then we're going to have a lambda x applied to something, but that's the programmer's fault, that's not our fault. So we can blame them. And then what's the other possible thing that might happen? So here, right, the way we've modified this CPS is that when we're translating both computations, which take the continuation, and then we're going to put the continuation to where it needs to go. Right, so this is a form of doing this. I think the earliest one was from Plotkin. He had a colon translation was the name because he used a colon in the way that he wrote it. But it was just saying, you know, if we translate a computation, you need to give me the continuation. I'll put it in the right place. And in these cases for application, we sort of create a continuation that is a lambda, which might get applied to a value, but that doesn't actually happen because the only time we supply a lambda continuation to this translation is if the term we're translating is not a value. So we never get this interaction between this lambda getting applied to a value. And again, the nice thing about scheme and racket is we can actually test this out. So you can take this translation. It's definitely more complicated. There's a lot more lines to it. But you don't have to worry too much about how it works. You can just dutifully translate this into some more macros, and that takes some more time. So don't worry too much about the details. But you know, if you're interested, you can look at the paper. But then actually test it out. So if we have this more refined translation that tries to avoid the administrative reductions while expansion happens, and we ask for the output, this is much, much cleaner. It's pretty much about the most direct form you could get, right? This is a normal form. Without supplying something for kf or x, there's no more reductions that could happen. So we really can't do any better. This is the optimal output. And so at this point, it's just you have to know a little bit about how CPS works. So I mean, I'm not saying it's great, but you're not going to do any better than this. So this is kind of the idea. So what's the problem here? So this is fine for these kinds of small examples, but it's not really, it doesn't scale very well, right? So this is a very monolithic approach. And if you want to add more language features, even the translation itself kind of blows up in size, right? Even this small little language which had only 3 things, variables, lambdas, and applications, what was a 3 different case translation became, I don't know, half a dozen, if not more. It's a lot more details to go through. And that's not super great, right? So really, ideally, if we're kind of doing this sort of stuff, a more modular style is better for your own reuse, for the users, and things like that. So how can we do something a little bit more modular is to, well, think about this, right? So especially in other languages like Haskell, what's very popular, the continuation monad. So you can think about the monadic interface, which breaks down what CPS does into these smaller primitive operations, and then you stitch those together, right? So what is the result of translating a term is going to be some function that takes the continuation, calculates the answer. And then the main ways that we use these is after I run a computation, we'll follow up by a continuation. And that's really just function application, right? And the continuation itself, if I want to use the continuation, we'll resume it with some number of values as arguments. And then again, that's function application. And then we also have the actual ways to kind of build these from small parts, which are return and bind traditionally. And this is kind of like the base thing. And then if you want to run a CPS term itself, then after it's done, we pass in the identity function, which just returns the final result that it calculated. And so you might think a little bit, I'll just kind of head off the question, you might like, why bother with after and resume? They are just function application. This is a very important tool we will use later. So keep that in mind. I know that it's trivial now, and they will not be in a little bit. So if you're wondering, that is important. But think it's this kind of, we have a concrete set of operations for both introducing, right, return and bind, make new continuation passing style terms or computations, and after and resume, use them. Okay. So advantage here is it's a lot easier to extend this kind of style with more stuff, with more language features, right? We don't have to have this one giant monolithic macro that takes a big grammar and then crunches it all down. We just have these parts that we can stitch together. And then you could extend it with lots of things, do notation and multiple argument functions and blah, 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 blah. Okay, so what's an example? So do notation is really nice for being able to actually use these and stitch them together. Wouldn't that be nice to have? So here's kind of an example of how these small little things work together. So here I wrote a macro called chain, and it's really just right association. So if you give me a sequence of operations, right? We can just nest them to the right. So if so each of these operations are going to take a number of arguments, and they're missing the last one because they apply to the thing on the right. And then here we've got the kind of do style, like let value. This is the left arrow of Haskell's do notation, which means run the computation and get the result. And that's just a bind, right? We just bind the name to so it's like, okay, this is a more comfortable way to write the same thing. It's a very short rule. And then you can do do notation, right? We can just chain a bunch of things together. So we can, if, what is H here? I think, oh no, H is the name, so we're taking some computation and then actually running it, and then we, with using let val, and then here there's a normal scheme let, nothing unusual here, that we make a name, and then we do some more steps, and finally we return y. Right, so we can do this with a little sequence. So this is kind of the idea of why it's interesting. And we can still, write the original CPS transformation using these primitives, so we're doing a little bit less by hand, right? So same kind of idea, but it's a little bit more general now, right? So here I've got, instead of lambda taking always one argument, it's all of the param forms that Scheme supports, right? So any number of arguments, or maybe there's a rest parameter, or maybe you just take them all, right? So however that works. And then also if you apply a function to as many arguments as you want, there's another separate macro call which just unfolds all of that thing. And then here I've added return as sort of special keyword in case you just want to say, run this expression outside of the CPS and return the value within. Okay, and then there's some extra helpers. Like for example, ret lambda means just return the lambda, things like that. Okay, so that's all nice and it's all modular, but then what happens again? When we expand the code, it's maybe even worse, which is not nice. So there seems to be this tension between compositionality, modularity, versus having concise, nice output, doing these optimizations and stuff like that. So can we have our cake and eat it too? So this is really about like trying to establish the modularity, compositional stuff, and then breaking that when we want to do these kinds of optimizations in the macro process. And so what's kind of the problem? So here, for example, it's a very small example. If I say, well, I want to return a value, and then after that, I want to pass the result to the continuation, really, I just want to apply the continuation to the value. But as I wrote it, these kind of expand on their own, and I get this kind of messy code, which has the extra intermediate step that I don't want. And really what I would want to say is just fast forward that and just say immediately apply the continuation to the value. Right? But how do we get after to look ahead and sort of anticipate this next step, that after I am done with the return in particular, not just in general, we want to kind of specialize that. And so the first kind of step is to say, well, here's a pair of, I make a new CPS computation using return, and then I immediately use it with an after. And then let's define the special case for what that means of that combination of use and introduction all at once. And so define what that shortcut should be, right? So we can say what that is. So this is just saying, well, after I return a value, and I need to continue with k, then that's the same thing as resuming k with this value. That's like a special case. If I see these two right next to each other, I want to do that. And then the general case, we can just generate by eta expansion. So you don't really have to write it twice. We kind of do, but the general case is always just going to say, here's the eta expanded form. So if I don't have the k at the moment, then just be a lambda that takes the k, and then do the general, or do the specialized case. And you do the same thing with bind, right? After bind is saying, well, I need to run m, bind the result to f, and then after that, pass the result of that to k. And if we're doing all of that, right, if I know that what the continuation is at the time that we are expanding the macro and creating the syntax, then we get these things. And there's two cases. So here, just look at the second case first, which is the more general case. I wish I could write it first, but we have to do the fall through at the end. So saying after we bind to continue with the k after, we say, well, the first thing we have to do is do m. And then after that, we bind the result to x and pass the x to f. And then when that's done, after that, we do the k. And because we have at compile time or at expansion time, we know what that k is, we can just stitch it in. We don't have to bind it to a lambda here. And this is sort of foreshadowing what the trick is, and it's maybe a little gross, is that we've got this lambda that we're looking at, and we're looking ahead and saying, well, if I'm binding to a lambda, I don't even need to do the application. I could just make it a let directly. That's kind of what the trick is going to be, is that we're going to look ahead a little bit and do this. And then we can do the general form as well. So this is the pattern in general. You have a use of something and the introduction through some operation. We want a shortcut to an after form. And so how do we do this in general is that it's these pairs of intro and eliminations. And after and resume themselves can look ahead and pull that out and do the shortcut. And get now the optimized form. So you can do the compositional definition, we still get the fully optimized CPS form. Okay, but there's still slightly another problem. This then becomes what after looks like. Every special case we have of a rewrite shortcutting, there's a lot of them, and they all are essentially of this form. After I return a value, I turn into after return. After I bind a value, I do that. After a let value, I've got a special form for that. And if none of those apply, I just do the normal thing. Okay, that's very redundant and kind of closed off, so not ideal. But they have this predictable pattern, right? It's always after some operation with arguments, I turn into some other specialized macro. And so we can capture that logic in just a big rewrite table of whatever cases we want. And then this is the worst macro magic. Definitely don't try to understand it right now, but it's doing the general case of looking up in the lookup table to see if I have a rewrite, performing that, and if I can't do a special rewrite, we just do the normal thing. And the advantage of this is, well, it's easier to write as a macro writer as long as you've got the magic, but also the user can extend it with new rewrites. So as a quick conclusion to wrap up, these are like kind of small examples, but yesterday I talked about at Olivier Fest some co-pattern matching code. And so I use this as part of debugging that. And you can try to quantitatively talk about how much smaller the programs, but I can say the user experience was I could actually understand what the expanded macros meant. And I could actually debug them. So that's the real reason I wanted to do this and kind of tell other people how they can do that too. So this kind of eases that tension. You can have both modularity and nice, efficient things by breaking that barrier using these kinds of rewrites things. So all right, that's it. I think I'll leave it there and answer any questions you might have.
Any questions? I can pass the mic, if so. Okay. Oh, okay. Student volunteer will, actually.
Thank you. Thanks for a very clear talk. So you're attempting to make two things coexist. The fact that the CPS transform as in one pass is a big step process, and then you want to achieve it somehow with self-organizing local processes, and then you kind of bend over backwards to make all of that fit in a beautifully elegant way. There is a global property of the source program, which is the expression in tail position?
Is the expression in tail position?
And if it is, and if you have the ability to detect that, then there is no need for but you have that information. It's a static property, okay? And then rather than having your local macros that is testing essentially am I in tail position or not, and if that's the case, then I don't need to put a lambda, and otherwise I do, and that would buy you much. Now that's again the initial tension between you want to do something global by assembling a lot of local things and make them self-organized in some sense, but still you're losing kind of technically the property that is in tail position. You're not exploiting it, and if you could, then everything which is around what you do if it's in tail position and what's not, you get for free. Without testing locally, because it's a global property. So couldn't you have something like an inherited attribute that says, I'm in a tail context, because essentially that's what part of what you do is doing. Do you agree?
So I think there's a couple things there. So there's a slightly different way you can kind of organize this, right? So rather than do the testing, you can kind of say like, oh, if I already have it, I think that's what you mean by tail condition, or tail position, right? We don't have to do the rewrite, which you can do it that way, but there is something else that you do lose, I think, which is, let's go to this one, maybe? Yeah, maybe here, is then you can kind of, this can change. So the after can get eliminated, but then also the resume can get eliminated, and these can go back and forth.
But
So
only if it's in tail position. If it's not in tail position, you want all of that. But if you can distinguish that a priori, do you not then avoid all the tests, the local test?
Maybe. I'm also not sure if I can detect that in general during macro expansion.
During macro expansion, indeed, that's a challenge.
Yeah. So this is specifically about macro expansion. So if you're in a more theoretical setting, you can have a lot more tricks in your toolbox.
Yeah, sure.
Yeah.
The challenge is that you want a bunch of local rewrite rules to self-organize to obtain a global property.
And it's just kind of thinking of it as like, when you're doing that, you can either change your translation or you can do rewrites usually after. This is kind of mixing those rewrites into the translation time without really changing the translation in the same sense. Yeah.
Now, distinguishing whether, like for applications who have value computation, computation, that was also done in Sabre and Felicen's very initial CPS transform.
Yeah, a bunch of people have done that. Yeah, I didn't cite it here, but yeah.
And that's losing compositionality. So it's a trade-off at every step. That's what makes it fascinating.
It's definitely trade-offs, yeah.
Question over here. Thank you.
If during macro expansion you had access to see the context in which you are expanding, would that allow you to eliminate these administrative reductions in a more simple way?
It might be, right? So it's almost like the return wants to know that if I'm in this context, then I could do that. And instead we have to wait until the context is there. So that might help. Yeah, I think so. Yeah, and that's kind of why we had to introduce this sort of what was a trivial macro, because that's what's actually going to do all the logic. And this is kind of like, we wouldn't need that if we could just detect if we were in tail position, which is not normally something you have in macro expansion. So we're kind of inventing that information, and it's a little bit roundabout, but that might be another way to do it if you had that.
So we need macro expansion with context.
Yeah, that might help. I don't know exactly how that'd look like, but that might make it a little bit simpler, yeah.
I have a few ideas.
Yeah.
I forgot to ask, what about conditional expressions when you intention to duplicate the context?
So for those, so that is something that came up in the real use case for copatterns, and all the ones I showed, you don't duplicate it, and reasonably you should be very careful not to duplicate serious code. And so basically for that, there's like kind of I had separate ones saying like, I'm willing to inline this, which is usually because it's just an identifier. And if the user gives me something, so the ones that the users really use, whatever they give me, I'm assuming is very large. And so that initially gets bound to one variable, but then that gets copied wherever because it's just a single identifier. Maybe, yeah. I don't know, but duplicating inflates the code size then, so that's another challenge.
And it doesn't matter if you're in tail position because the continuation is just an identifier.
Oh, I see what you're saying. Yes, if it's just an identifier, then that's fine, yeah.
So again, an a priori, it's all about inherited properties versus synthesized properties. Yes. And you're trying to build everything on synthesizing properties and then trying to manage, and that's the essence of the fight. If you were to do both, inherit some, synthesize some, then you would be in a much sweeter spot where I believe but on the other hand, you're doing it with macros. So
yeah, I'm doing it with macros. Yes, if I didn't have to do it with macros, there's so many easier ways. This is just how to get it to work with macros. That's the point of the talk.
Okay, let's have Sean start setting up. All right, next we'll have Fast and Extensible Hybrid Embeddings with Micros by Sean Bakirnia.
type checker when, that sounds a bit more loud, when we're doing type checking. So if we don't care about performance, then we're not going to be able to type check anything, really. And because this is a research language, we care about it being extensible so that we can play around with changes to our typing judgments and stuff like that. And really, this talk is about these three properties. How do we get a framework that is interoperable, extensible, and has performant compilation? Now, this isn't just a toy problem. There are people in the real world who want languages that are both extensible and quick to compile. One such example might be something like Agda. Plenty of new type theories are tried out in Agda. Some are like cubical, rewriting. And another language that has a large community of extensions is WASM. So most recently, the garbage collection and multi-memory are in the pipeline. But more importantly, for both of these examples, performance really matters. So Agda's got a complex dependent type system, so it's got the same problem that we do. And WASM is just-in-time compiled, oftentimes over the web while people are waiting. So it's important that it compiles quickly. Cool. So back to our three goals. Each of these requirements needs maybe a bit more clarification. So because we want interoperability with Racket, what this really means is that we need a shallow embedding. So what shallow embeddings do is that they let us mix host and object language syntax, which for our purposes we need in order to understand the implications of our gradual type system. And what this looks like really is that, for example, if both Racket and FOWL have a concept of vectors, we can call vector operations from one language on vector representations from the other. On the topic of extensibility, I want to clarify that there's a distinction here between extensions and modifications. So when I mean extension in this talk, what I really mean is separate compilation. So we have some base language, and extending that language means that you don't necessarily have to destroy the properties of the base language. By contrast, a modification is a change that's made to the base language which overwrites the semantics of the original version. So with something like this, I would argue that these are more modified languages, because even if you can turn off features with compiler flags, the implementation of these languages still needs to be carefully managed by the language implementer, and at some point in these language implementations, the coexistence of these possible sets of features still needs to be carefully handled. And lastly, we're only worrying about compile time performance here because it's far more dependent on the compiler framework, and it's far more important for complicated type systems. And runtime performance of a language is a lot more dependent generally on a particular implementation or particular optimizations that are performed. So, all right, here's where we're at. Right now, we've got some programming patterns that we can use to implement all this. But in the future, what we really want to do is package these patterns into some abstractions that make it a lot more straightforward for people who want to implement their own languages to use our work. And yeah, eventually, hopefully, this might look like something like a meta DSL. Okay, now we can update our roadmap. And let's talk about existing approaches. But first, pop quiz. So when we're compiling, how would we like to represent our programs? Well, I've been told a lot that programs are data, but I guess there might also be syntax, because they are just a bunch of symbols, but we traverse them like data. But, well, maybe if we understand better what we mean by each of those, we'll be able to pick. So let's dive into that a little bit. There are really two kinds of syntax that we usually think about. The first is concrete syntax, just program text, whatever your favorite encoding is. But especially in Scheme and Racket, when we talk about syntax, we also mean abstract syntax. So stuff like S expressions, which are just a tree of arbitrary symbols. It's a very permissive representation. And very importantly for this talk, a valid S expression is not necessarily a program in any particular language. I want to contrast that with data, which I'll be using to mean really well-specified IR, which only admits terms of a particular language. So instead of arbitrary trees, we have something like tagged terms with very well-defined children. And if I use syntax and data in the rest of the talk, I mean these two categories. Cool. Well, now that we've made that distinction, I think it's still important to take a look at what some related work does before we decide. 3 related works drove our design decisions here. Turnstile Plus is a Racket library that allows you to encode type systems as macros. LMS is a Scala library which gives you staged metaprogramming. It lets you define languages in terms of Scala classes. And Syntax Spec is another related work that is also built on top of Racket. It gives you the ability to extend a language using hydronic macros. And interestingly enough, all of these 3 have a different way of representing programs. So Turnstile Plus keeps everything in what we'd think of as syntax. LMS, the entire pipeline is this structured IR, which has which you need to define for each language. So that qualifies in our idea of data. And Syntax Spec does a bit of both. The macro system lives in syntax land, and then eventually you do actually have to convert everything to some static IR. And in each of these tools, this is where you'd perform program transformations like optimizations or type checking. And in the case of Turnstile Plus and LMS, these transformations are extensible. So it's possible to change the type theory of the language without clobbering a base language. But in Syntax Spec, while it is possible to extend the syntax of a language using these hydronic macros, the transformations on data, like type checking and whatever else one might want to do, are not extensible. So each of these, in different ways, fails to hit all of those 3 metrics that we're interested in. But we start to look at this graph here, and we start to notice that, well, you know, maybe we can kind of take the syntax part of Turnstile Plus, which is extensible, and then maybe, you know, go and steal a little bit of the data part of LMS, and get something that will work for us, that will be both fast, extensible, and have good interoperability. And you can also think about this as making the data part of Syntax Spec extensible, you know, either or. All right, so back to our quiz. Well, I guess both. We should pick both. In other words, what we really want is a hybrid embedding. So we have something that looks to Racket like it's Racket syntax, but in the back end, we have a AST that we've constructed that we can churn on, much like LMS. Okay. Nice. So how do we do it? Well, first we need to talk about macros and micros. And to talk about macros, we'll start by taking a look at how Racket represents syntax. You're all familiar with S expressions. Basically, Racket syntax objects, which its macro system operates on, are just S expressions with some scope information. And both Racket and us use that to resolve binding. So, you know, quick refresher on macros. Say we have a list macro. We spit out this sequence of cons. Really, the important thing here is that macros are syntax-to-syntax transformers. And when we look at how something like maybe Turnstile Plus uses macros, really what happens is that you start with some program text. Racket's reader does the job of turning that into syntax objects for us. And then Turnstile Plus just loops in this macro expander in order to resolve all of its typing judgments. And finally, at the end, spit out core Racket, which is understood by Racket's compiler, and then executes. Well, this is great. Both of these are nice and extensible. Racket's reader and macros are very easy to extend. You can use Racket's module system to do this and separate your languages. All well and good. But all of the work is here. And unfortunately, in the case of Turnstile Plus, because it's modeling type checking operations, the expansion of order of macros conflicts with the order of type checking. So to make matters worse, what happens is that in order to encode these typing judgments, more macros are emitted during type checking, which are then expanded. And anyways, this blows up. And to make it even worse, Racket's syntax objects in particular are represented using linked lists. So they have quite poor access properties, and things can start to get quite slow. All right, so if macros are the problem, then I guess let's get rid of them. But we've kind of got a hole here. Well, you know it already. We're putting micros. But, well, what are they? Okay, Let's take a look at our list again and say this isn't a macro, say that it's micro instead. We might expand that into something more like this. So we've got a set of structures now, and notice that there's no hashtag here. So this is not syntax, this is data. And indeed, that's what macros are. They're expanders from syntax to data, and this is not a new idea. Sriram's PhD thesis covered this. But we use a different representation for our data IR. We don't actually use Racket syntax objects. What we use is Racket structs. So these are just named records, really. In this case, the name of this record is construct. Maybe it has two fields, car and cutter. And in addition to that, Racket also gives you the ability to attach generic methods to these structures. In this case, we have something that we'll call elaborate, and then we can specify the implementation of elaborate for cons specifically, just attached to the definition of cons. So we use these generics in our circumstance to encode our typing judgments and encode any other transformations that we'd like to perform on our data AST. So in the case of elaborate, this is a particularly important one that every language that uses our framework will need to implement, because this is the very last transformation that we perform to spit back out Racket syntax that we can actually run. So the elaborate generic is what you use to encode your runtime semantics, but you can have plenty of generics for whatever you'd like to do, including a separate one for type checking, or if you have bidirectional typing, maybe you'll have two. Anyways. These are features that we'll use to build a language. So first of all, turns out that you need a bit more than just micros to fill this gap. So what we really need is 3 separate steps. You may be looking at this and thinking, wait a second, you got rid of macros, but you're adding them back in. And that's because it's still useful to have some macro functionality for stuff like syntactic sugar. Note that we never loop through the macros. We do one macro expansion pass for whatever syntactic sugar might be useful, but we don't use macros to encode typing judgments or program transformations. Neither do we use micros to do that. Micros simply take a syntax object and then spit out our struct AST. And then, using the generics that we talked about, we loop over that struct AST, perform program transformations, perform type checking, and then at the end, via that specific elaborate generic, we spit out our syntax objects that are in Racket core that are the actual runtime behavior of our programs. Cool, so all the work is here. And it happens on a mutable data structure that we can update in place. Our syntax is only expanded once, and to top it off, Racket structures have O of 1 access on any fields. So things are looking pretty good. And this isn't just theoretical. We also built a dependently typed language using this framework, and we are about 100 times faster than Turnstile Plus on a suite of dependently typed benchmarks. That thing right at the bottom there is the fastest dependently typed type checker that we know of. We're not quite that fast. We're still about 3 orders of magnitude slower than that. But we are only 1 order of magnitude slower than stuff like Lean or Agda, which are modern in production dependently typed languages. All right, so we made it fast, but we still need to make each of these extensible. Well, Racket does both of the first ones, and with some ad hoc programming patterns, we can do the second ones. And we did indeed manage to extend our language in some pretty cool ways, including modeling even the gradually typed part of it as an extension to a non-gradual dependently typed calculus. But that's not very nice. So we'd like to make each of these different parts of our language extensible more neatly. We'd like some nice abstractions that package up what we really needed to do there. So again, the reader and macros are extensible, but because our struct AST is not inherently permissive, extending micros and our struct transformations takes a bit more work. And really, we nailed down 3 abstractions that are needed to make this work. For micros, we need extensible micros. And for our AST transformations, we need some way to extend structs and some way to extend generics. And really, each of these maps to a different class of extensibility in our object language. So with extensible micros, you get extensible language syntax. And with extensible structs, you can extend individual transformations on particular language terms. And with extensible generics, you can add new classes of transformations. Cool. So let's take a look at the first of those abstractions. Just as a refresher, with macros, you expand till you run out of them. All well and good. But interestingly enough, to get a hybrid embedding with micros, we have another interesting problem, which is that we now need to recognize which syntax objects are actually part of our language and which aren't. So in this case, if we expand this list micro, okay, we need a structure that's representing the list term. But then, well, we only have the list micro here. 1, 2, and 3 are just racket core. So I guess maybe we put racket core syntax here, but wait a second, that's not an IRR. That's not wrapped. We have no way of attaching semantics to this. So really, sometimes we want to actually be able to recognize racket core IR as well and turn those into our AST. And just a side note here, it's a bit more complicated. We sometimes want to keep the source syntax around, especially for binding. And if you want to see the backup slides, you can ask about it. But the two ideas are basically we need to recognize an AST extensively, and we need to be able to shadow and add new macros so that we can add new language terms. All right, so extensible structs, a bit more straightforward. Say we have this lambda, and it expands into an AST. Cool. This is untyped, though, and we talked about types a lot, so maybe we want to add types. And to do that, we're going to need to add some annotations to our syntax. Okay, I believe I can do that with extensible macros, but that means that we'll need to annotate some of our variables so that we can perform type checking, right? So okay, we put nat in there, but that means we need new fields. So if we look at what the struct might look like, say it's just got one field symbol, then we'll need to add a new field type, and indeed we might even need to change the implementation of some of the generics so that now we use this type information. Perhaps we want to preserve it across modules, whatever else. In particular, we need to change generic implementations, and we need to change the fields that particular structs have. Cool. So we've added types to the structs now, but maybe we want to actually use them. So we'll need some way to add new generics. We need to add a check generic in this case so that we can type check our language forms. And in addition, we might even need to change the signatures of existing generics. So say maybe elaborate is now type directed. This is a bit of a contrived example, but in general, we did need the ability to change existing generic features, especially for the gradual typing extension. But these are the two requirements that we settled on for an extensible generics abstraction. All right, so we've kind of figured out what we want. Let's try to implement it. Turns out we can do micros. That's not too bad. But the other two are a bit more difficult. We've got a pretty good idea of how to implement extensible structs. In particular, the thing that is really tricky for extensible structs is that Racket has this concept of structure properties, and these are a bit harder to proxy. But extensible generics kind of uses these a lot. And because we haven't figured them out for extensible structs, extensible generics have us quite stumped. So just to wrap things up, if you want hybrid embedded languages that are extensible and compile quickly, you can use micros to elaborate a shallow embedding to a structure IR. You can then use generics to type check, transform, and emit host language code. And then, after we figure it out, you can use our abstractions to make it extensible. For now, we have some programming patterns to let you do that, but really what we'd like out of this talk is to be able to chat and see what ideas you all might have for how we might implement these abstractions. All right, if you found this interesting, a lot of my colleagues have given talks on related topics. You can catch the recordings if they happened in the past. Thank you very much for coming.
We have a question in the back here.
Very nice talk. It's very good to see someone try to figure out forms of extensibility that go beyond macros. Macros are very powerful for extension, but there are other ways to extend that macros can't always reach. It's good to see that. Does the work you're doing have to deal with hygiene?
We don't tackle hygiene specifically. Indeed, syntax spec does, which is one big difference. They're concerned specifically with providing functionality for having hygienic macros in between languages so that you can't use language forms that are not in your language. So for example, this might be useful for our gradual embedding, but right now with this work, we were not concerned with hygiene in between languages. We have the hygiene guarantees of Racket's macro system for our surface macros, just our sugar macros, but we were specifically worried about being able to model our extensions and did not concern ourselves with the micro hygiene system.
So do you mean that you're ignoring hygiene currently, or just that it doesn't interact with the layer at which you're operating?
We inherit hygiene in a lexical sense from Racket's macro system, which we use to implement our micros. We do not have a concept of hygiene akin to something like syntax spec in between different languages.
Okay. Second question, if I may. You mentioned you're working in a dependently typed language. Yep. The natural thing there is proofs. And so I'm wondering if, similar to my question in the last talk, if you can have access to some sort of element of your context. So in a proof, if you want to write a macro that represents a tactic, it would be nice if that macro could know what type is being expected by the surrounding context.
Well, there are two parts to this question. First of all, when we're talking about a module that is specifically in maybe like just a foul module, because it's a hybrid embedding, we'll have a deep representation of the AST, and then while I'm not familiar with the specific requirements of tactics, I would imagine that because we have a full program available to us at that point, we'd be able to perform whatever context-dependent analyses are required. Intermodule, things get a bit more interesting. We need to find some way of compiling to a Racket core language that allows us to preserve some of this typing information so that it can be read back by whatever other module needs to be compiled on top of this base module. And that is something that we've developed our system with in mind, but since we haven't written something like a tactic system, I can't guarantee that is expressible. But within a module, I feel reasonably certain that would be possible.
Okay, thank you.
We have time for a quick question.
Afterwards, yeah.
Yeah, I was curious, the problems you're having with, or maybe not problems, but future work with structs, is that dependent on your choice of representation of the IR as structs? Like, if you rewrote it to be represented as classes, would that change anything or change nothing?
For example, LMS has a class implementation. I believe Ziggurat also has something like classes. It has objects in the background. That eases some of the concerns with regards to implementing the abstractions. But internally, we ran some performance tests and noticed that for Racket particularly, we had quite a significant overhead when using objects, specifically memory footprint and also access time. So that's what led us a bit towards structs.
Yeah, we can talk about that. I just want to know if it would fix extensibility issues like the extensible generics.
It does help at the cost of performance.
Gotcha, thanks.
Yeah. All right, let's thank Sean again. All right. Speaking of hygiene, next we have Hygienic Macros via Staged Environment Machines by Witu Murase.
Hi, I'm very happy to be here and have opportunity to talk about our ongoing project so it's about the relationship between hygienic macros and staged computation. So basically, it is known fact that hygienic procedure macros and staged computation are somewhat similar. So it's about generating code fragments at compile time stage that will run at runtime stages. So, and So hygienic procedure macros are more about language design or implementation thing. So, and it has less known theory, so in the context of lambda calculus. On the other hand, multi-stage computation arises from lambda calculus context. So it's natural idea to apply multi-stage computation to hygienic macros to establish hygienic macros with solid theoretical background. So there are some proposals, and they are successful to some extent, but so there are still some gap between these two. And in this talk, I want to highlight the difference or similarity between alpha renaming in multi-stage computation and explicit renaming. So this is a hygienic facility in hygienic macros. So let me quickly introduce this explicit renaming thing and alpha renaming. So, macro is about extending the syntax of the host language by macro expansion. So if we want to have or macro that takes first argument, if it's true, it just returns that result. Otherwise, it evaluates and returns the second argument. Then we can define this or macro by providing this expand result. So it evaluates the first argument, binds it to temp, then we just use the if statement. So it just works. But so here we see that it introduced new binding with named temp, which introduce sometimes the issue. So let's say this example. So here we use or macro with the variable temp. So this seems working, but it doesn't because or macro inserts new binding with the same name, which blocks the binding of outside. Then as a result, this temp refers to this one, which is not expected. So that's how name conflicts makes macros unexpectedly. So basically, that's the problem what hygienic macros tries to resolve. And so idea is very basic. So for each binding, we introduce new names, unique names for these bindings. So now we can see that these temp1 and temp2, so they are originally the same name temp, but they are renamed to unique names. Then in this way, we can ensure that bindings inserted by macros will not block other bindings. So although this idea is very simple, so there are many ways to implement or achieve hygienic macros. So there are many mechanisms or algorithms to achieve hygienic macros. And here, in this talk, I want to highlight explicit renaming macros. So because it is one of the most primitive and concise interface for hygienic macros. So in explicit renaming macros, or macro is written in this big thing. So it's a bit bothersome, but because it's a very primitive interface. So basically, it's procedure macro. It means that or macro is defined as a function in the host language that takes source expression and it returns an expanded expression. So you can see this quotes generates expanded expression. And you can also see that this lambda takes two more arguments. So that plays an essential role to achieve hygiene. And let's focus on this renaming function. So this is a function that takes raw symbols and it resolves its name to unique name corresponding to its syntactic environment. So for example, if we call renaming function with let, the symbol let, then, so in this context, let means that in standard library, then renaming function returns a unique name that always looks at letter in the standard library. And if we give temp, so in this case, temp is not defined in this context, then renaming function just returns unique name so that it will not conflict with other bindings occurring from temp. So that's pretty much, so explicit renaming is basically procedure macros, and it uses renaming function that resolves names to unique names. And programmers have responsibility to perform appropriate renaming. So yeah, that's the basic idea of explicit renaming. Okay, then let's look at alpha renaming in multi-stage computation. So, multi-stage computation, so here I mean query quotation-based language like MetaML or MetaOCaml. So this is MetaOCaml program that does very similar operation as OR macro. And so you can see it has query quotation syntax. So it's MetaOCaml way to represent query quotation. And it generates a program that behaves as OR. But here you can see this temp has binding relation. And so alpha renaming basically says that we can just rename these names with binding relation at any time. So we can rename this to ABC or PPP. And so all these programs are just same under alpha equivalence. Okay, then let's consider evaluating this program. So here we can see two different binding relations there with same name. So if we don't rename them, then it will conflict. So we just perform renaming on one of the binding. Then that's perfect. So it doesn't break binding relation. And yeah, so alpha renaming is just says that you can rename bindings to avoid conflict. And so both alpha renaming and explicit renaming make sense, but they appear very different because explicit renaming is very explicit procedure where a programmer can manually perform renaming. Meanwhile, alpha renaming is very implicit one, so it is separated from operational semantics, and so it can be performed non-deterministically. So I think many people think explicit renaming and alpha renaming are just different things. But so in this talk, what I propose is adding intermediate step to compare them. So here, the intermediate step I add is, so it's also multi-stage computation, but in more elaborate operational semantics. So here, I call it environmental massing semantics. So in this staged variant of environmental massing semantics, then alpha renaming is elaborated to more elaborated steps for renaming, and it is now explicit and deterministic, so it is much easier to compare these two. Okay, so let me quickly introduce how environmental massing semantics works in staged computation. So it is actually the intermediate state of evaluating staged program, unlike MetaOCaml programs. And this consists of 5 elements. So this yellow part is expression under evaluation. And we have level of that expression. So 0 is for runtime stage, and 1 for level inside code generation. And we have a deeper level for deeper nesting structure of code fragments. Okay, and we have evaluation context or continuation. And we have 2 environments. So this value environment is the standard one that maps variables and its corresponding value. And in addition, we have extra environment, which I call renaming environment. So that maps row names to its corresponding unique name. So basically, this plays important role to achieve hygiene. And let me quickly explain how this works. Okay. So when evaluating this program, then we first evaluate this one. So get the content of A, then embed it here. Then we get this as a generated code. Then after that, we look into let binding inside code. And at this point, so machine will generate new name. So temp1, and then it has new, so that mapping into renaming environment here. Then, so according to renaming environment, we perform renaming. So this temp is renamed to temp1, and this also renamed to temp1. Okay, then finally we get this code fragment, and so we can see that renaming is performed appropriately, and binding structure is kept. So yeah, that's pretty much the basic idea of environment massing with staged computation. then the step from dismissing to explicit renaming is somewhat straightforward. So in environment massing, variable name is automatically renamed to temp1 using renaming environment. But what if we introduce explicit reflective interface for renaming environment? So we have a rename function, and it takes a row symbol, then it returns a corresponding name according to renaming environment. Then it just returns to temp1, and so that's pretty much it. So the message in this talk is explicit renaming is. So it can be considered as a reflective interface to renaming environment. So going back to high-level description. So yeah, I just say that renaming function can be explained as reflective interface to explicit renaming. And also, the step from this one to this one, so elaborating semantics, is kind of standard technique in lambda calculus. So there are many work on this topic. But so especially talking about stage computation, there's work by Gay and Garcia that elaborates semantics of multi-stage computation. So they make environment massing semantics somewhat similar to our environment massing. Okay, and so that's pretty much about my talk. So you can check out my paper for more discussion about it. So I provide full semantics for staged environment massing. And so I made a draft design for abstract machine semantics for explicit renaming macros, but I'd say it is very incomplete because there are still many gaps between multi-stage computation and hygienic macros, so you can check out paper for discussion. Okay, and key takeaway, so basically, so explicit renaming might appear just an implementation detail, but I think it has a theoretical background, so that can be explained by alpha renaming. And the second message is, so here I quickly introduce staged environment massings, and I think it's very interesting subject object to dig in, but there's still little work on about that. So I think that's something that interesting to work on. And yeah, that's pretty much that I want to talk in this talk. So thank you for listening.
Any questions? We got plenty of time for them. In the back here?
At this rate, I should just sit in the front row. I like that you're exploring this work, and I want to talk to you more later about this. But what do you see in terms of where this work could go in terms of new features or functionalities that might be accessible with this sort of model of macros and hygiene?
Sorry, I didn't catch where.
Okay. What features do you think? What future results do you think that this model of hygiene could allow us to access?
What feature? Let me see. Not sure if I understand correctly, but so in future, I think coming up with full model for programming. So I want to come up with operational semantics for programming language with procedure macros. So basically, explicit renaming is hygienic macro, but so it is procedure macro. So it should include operational semantics of the host language. And so there are many formal models considered for hygienic macro expansion, but they usually don't include operational semantics of the host language. So it lacks the interaction between host language and hygienic macro expansion. So I want to make something that covers this area. So does that under your question?
Yes, thank you.
Any other questions? Okay, I'll ask one then. We have lots of experts in this room, and you said there's still some things missing. Do you want to speak a little bit about that, and maybe someone will try and find you in the break and
also
exchange
you
ideas?
For what is still missing?
Yes. Yeah,
okay.
Yeah.
So I said that so explicit renaming can be explained in perspective of stage environment mass things. But so the remaining gap between these two is, so basically hygienic macro is about expanding from S expression to expression. But in multi-stage computation, so they represent code in more opaque data. So that is generative code fragment. So these two are basically just different things. So the biggest difference is that so Quoto in multi-stage programming is structured data like AST, so where binding relation is very clear. Meanwhile, S expression is just so binary tree with where it can have symbols or maybe natural numbers or those atoms on leaf. And so we cannot find binding relation at the first sight. So only so the programmer can find binding relation. And so at present, I don't fully formalize this difference, and that's something I need to work on. Do I explain?
Yeah, that's great. So if anybody knows about binding, come find Rito. Any other questions? Maybe that came up from the discussion?
Jason He-Man, Seton Hall. We know the stories and discussions about explicit renaming versus implicit renaming in different hygienic macro systems. Now that we've got a way to relate certain kinds of multi-stage computation to procedural macros, and we know the pros and cons of various kinds of macro systems, is there an analogy between different kinds of multi-stage computations, and what can you say about that?
Sorry, I'm not quite sure what the point you want to ask. So could you rephrase?
We've got an analogy going this way.
Yeah.
And we've got relationships going this way. So complete the diagram for me.
I see. So yeah. So what you mean is, so there are different kinds of hygienic macro facilities. And you are interested in maybe what ideas in multi-stage computation corresponds to other macro facilities? Exactly. Okay. So basically, my idea is a bit different. So I think every macro facility can be derived from alpha renaming, hopefully. So I don't say it's possible, but so that's my conjecture. Then, so there may be, so derivation path might be a bit different, but so I believe, so every hygiene thing can be derived from alpha renaming.
Okay, thanks.
All right, let's thank Rito again. Okay. Next, we have Checking a Denotational Semantics of Scheme in AGDA by Peter Mosses.
Thank you. So this is going to be a talk with a fair amount of denotational semantics in it. I'll introduce denotational semantics briefly as a recap for those who are not familiar with it. There will also be some AGDA, and again, I'll try to explain the bits of AGDA that I'll be using. So please feel free to ask questions in the talk if there are things I've forgotten to explain. 1975 was a very significant year for you in the scheme community. It was essentially the birth of your favorite language. I guess it's still your favorite language. 50 years is a long time for a language to remain popular. And I've had great fun, not having previously read the scheme reports, digging back into them. It was also a significant year for me in that I completed my PhD in Oxford and a pretentious title, Mathematical Semantics, which was the original name of denotational semantics, and compiler generation. It wasn't so much about compilers, it was about partial evaluation and interpreters, but it looked like compilers if your machine code was lambda calculus. The final 50th anniversary that I'd like to recall is a sad one. My supervisor, Christopher Strachey, passed away that year. He was 58 years old, which at the time I was 26, and I thought that was really quite an old age, but now I'm 76, and I think a bit differently about how many years he missed. He was a tremendously influential person, especially in the 50s and 60s in the UK and internationally. This paper is dedicated to his memory. You'll find links to his biography in the proceedings, and also there's the Wikipedia page, which is also quite good about it. So I must admit that my primary interest in Scheme is not in using it as a programming language, but actually in its denotational semantics. That semantics is reasonably concise, and it's been remarkably stable since it was first developed by Jonathan Rees and Will Klinger in 1986. But it has some well-formedness issues, as I discovered recently when I started digging into it. Some of them are quite obvious, but others I didn't notice when I first read it, and I guess the people that proofread the standards haven't noticed them either, because they're still there after so many years. I've been experimenting with testing denotational semantics. I tried it first last year in connection with Jens Palsberg's Festschrift, where he had a denotational semantics of inheritance and some verification proofs. I tried formalizing that and found it wasn't actually quite as easy to embed denotational semantics in AGDA as I had hoped. But since then, I've tried to make it easier and simplify what I was doing then. So part of the talk today will be to present that shallow embedding. In the paper, the main ingredients of the paper are about the denotational semantics of Scheme, but also about the shallow embedding with using Scheme to illustrate how this embedding works. And then there are the well-formedness issues that the embedding has detected, or that were obvious in any case, and the suggested fixes. Apart from the main ingredients, you can also take some supplements. There's the artifact, which is linked from the ACM digital library page, which has all the AGDA code that is used in the embedding. There are also, on the DOI page, there are links to a couple of PDFs. One of them is a listing of the plain code without any comments for those that really like just to read code and not to know what it means. And then this what is in the AGDA community called a literate AGDA specification. This is not literate in Knuth's original sense as a web of unordered fragments that can be given in any stage and developed top-down or bottom-up or whatever. It's just an interspersed. Actually, the literate version contains, I think, all of the denotational semantics from the R5 RS standard for scheme as comments, and then you get the AGDA code corresponding to that bit of the standard to be able to compare it locally. Since the artifact was submitted, I've added some code, a makefile basically, to generate a website from the AGDA code, which you may find it more convenient to browse online, but of course the PDF is convenient offline or printed. Please give me feedback if you have any complaints about the website. It's an experimental website generation. So let's start off with the denotational semantics of scheme. And there have been quite a few versions. It started essentially with a paper by Steve Muchnick and Uwe Pleben back in 1980, and where they were comparing Lisp and scheme and also mentioned the difficulty of adding eval to scheme at the time. In 1984, Will Klinger had a very nice paper with denotational semantics of a sublanguage of scheme and a proof of correctness of a compiler for that language. Then the official standards, starting with the third revised report on scheme in 1986, up to the present day, so to speak, with 2013, the seventh revised report, all of them except the sixth revised report contained essentially the same denotational semantics with a few extra features like whether lists were mutable or immutable and a few other minor details like that. The status of whether null was truish or not changed from one version to another. But it was remarkably stable. If you look at the standards, you find that in the denotational semantics, they cite Joe Stoy's textbook. It's actually quite an ancient textbook by now. It's not available as far as I know, except behind a paywall from MIT Press. I'd like to point out that there is an excellent article by Bob Tennant, which basically covers all the ground that you need in a much more concise way in the communications of ACM, which is open access. The nice thing about denotational semantics is that actually you don't need to know anything about the foundations in order to write or read a denotational semantics. Somehow it's got a reputation of being quite scary these days, and it's no longer taught in undergraduate curricula as it used to be, but I'd like to try and dispel that scariness. However, you do need a bit of meta-notation for defining the abstract syntax of a language, for defining domains, and for defining semantic and auxiliary functions. In the scheme standards, they give you a little summary of what they think is the essential meta-notation to have in your mind when you read it, which is basically focused on the notation for sequences and omits to explain what plus or cross on domains actually is, but it doesn't really give you an introduction to the meta-notation. It assumes that you've already read Stoy's book, basically. The structure of the semantics is quite conventional: abstract syntax, domains, semantic functions, and auxiliary functions. For abstract syntax, it uses a grammar with sorts and also has meta-variables ranging over those sorts and productions. For domains, it names the domains and again introduces meta-variables that range over the values in the domains and gives the definitions just by equations, mutually recursive equations. The semantic functions have types which are generally mapping syntax sorts to domains, and then there's a semantic equation for each production that defines the denotation of that particular class of constructs in terms of its the denotations of its subterms. So now let's look at this shallow embedding and see how scary that is. AGDA, as you may know, some of it's already been mentioned today, AGDA is quite an advanced language, and I'm not going to be exploiting much of it in this talk. The main point that I'd like to highlight is that the arrow in AGDA is used both for function types and for lambda abstractions, which is a bit off-putting if you're used to using a dot to separate your variables from your, or a parenthesis to separate your variables from your body. I must admit, the first time I started reading AGDA specifications in POPL papers and things like that, it was one of the things that I was complaining about all the time, but I've grown used to it by now. So to start our shallow embedding in AGDA, let's just cheat blatantly by saying domains are just types. So the universe of domains is the universe of types, which is called set in AGDA. Don't think of these as finite sets, they're really just types. And we can introduce some metavariables, D and D, ranging over domains. The really controversial bit comes with these two postulates. AGDA users have been indoctrinated not to use postulates because postulates just can be automatically incorporated in proofs and, well, not automatically, but explicitly, and you have no sign that they've been used in the resulting statement of the proved proposition. This first postulate, saying that the bottom element is an element of D for arbitrary domains, means that that is an element of every type in AGDA, and AGDA includes an empty type. And to say that the empty type includes an element is blatantly unsound. However, that is not going to worry us at all. Similarly, for fix, we're going to say that for every function from an AGDA type D to itself, that function has a fixed point, which is obviously nonsense. I mean, successor function or identity, successor function doesn't have a fixed point. Fortunately, the unsoundness of these postulates has no effect on the AGDA type checker. The AGDA type checker just goes ahead and type checks things, disregarding whether these postulates are sound or not. And that's what makes this shallow embedding work so well. There are plenty more postulates. In fact, one of the reviewers bitterly complained in the reviews about the lack of justification of all these postulates. You see, they're all over the place. You can actually abbreviate them a bit more in AGDA if you want to, but I've done it on a line-by-line basis to emphasize how many there are. But this is just the standard domain notation that one has operators for that, so you can use in equations. Now let's look at the various pieces of the shallow embedding. So for abstract syntax, this is how it looks in the notation used in the scheme standards. It's been the fixed notation in all the standards with something that looks pretty much like a BNF grammar, as is pretty close to what is used in Stoy's book or in denotational semantics generally. The AGDA embedding is something I'm less happy about. It's not as direct as I would like it to be because AGDA does not support these kind of grammars that we use in denotational semantics. There are also a couple of irritations. AGDA doesn't have implicit coercions, so we need to have explicit constructors for constants and identifiers. And AGDA doesn't even allow you to use ordinary parentheses as notation for constructors. So I'm using banana brackets. And just, it doesn't allow to have adjacent holes in constructors, or one needs to have some terminal symbol or concrete token in between, and I'm just using something that looks like a space in the standard Unicode. But otherwise, it's a one-to-one correspondence, and rather than using metavariables, we actually have to use the types of the arguments in the specification. Now let's look at domain equations, which are a bit more interesting. And these are the domain equations from the 5th revised report in the denotational semantics of scheme. And the AGDA version has basically an equation for each of the equations in the original that looks pretty similar. It's using pluses and crosses and things like that. Except that I've commented out one of them, the one for expressed values, because that AGDA doesn't like cycles between type definitions, especially if they're constant types. It just goes into non-termination in the type checker. And so we have to break that loop somewhere, and that's a very convenient place to break that loop because we can exploit the injections and projections between that sum type and its summans, we have to use those anyway in AGDA and in the AGDA embedding, and we'll be able to get between those summans and E just using those operations that we'll introduce in a moment. For all the meta-variables and the names of the domains, it's a bit more tedious, and we're also distinguishing between the set MISC of miscellaneous values and the flat domain that's constructed from it by adding a bottom element. These are the injections and projections that we're going to make explicit. So let's see how it looks. I hope this convinces you that it's a fairly shallow embedding. You see the version from the report at the top, and at the bottom you see the AGDA version. Okay, the dot has changed to an arrow, and we've had to insert spaces between our Greek letters to stop AGDA thinking that there was multiple letter words. And we've also incorporated the double bracket notation in the operator symbol, the mixed fix notation for the semantic function. But really, these are very trivial changes, and otherwise, it's an on-the-nose shallow embedding. So this is, of course, I've chosen on the slide the simplest possible semantic equation. There are some much bigger semantic equations in the scheme standard, and you'll find that actually they also translate very straightforwardly into lambda notation. So there's also some auxiliary functions. We see the function truish that's defined here. We'll come back to that in a moment, but let me just say that for many of the auxiliary functions, again, the definitions, it's delightful with AGDA that you can just use exactly the same notation for introducing the name of the function, giving its type, and then giving it an equation that defines that. Well, almost. So look at the definition of list. Well, that's a very neat definition in the original standard. It's not quite so neat here. First of all, there is the recursion on list in the denotational semantics, which is perfectly okay. You can define functions recursively. We define our semantic functions recursively. Also, auxiliary functions can be defined recursively. But in AGDA, if you define a function recursively in terms of itself, then it has to be inductive so that the type checker can terminate and know that you're not defining a non-terminating function. So we make an explicit fixed point here, which doesn't actually cost us very much. We just have to introduce a separate name and an explicit fixed point operator that's highlighted there. Moreover, in the auxiliary function definitions in the standard, it's rather haphazard whether functions are defined before they're used or not. Again, that's something that you don't really care too much about in denotational semantics, the order in which definitions are given. It's just a big mathematical definition. As in mathematics, you can just either do top-down or bottom-up or mix or whatever. So it's not wrong in the standard to do that, but AGDA is very much a declaration before use language. So you can define things mutually recursively, providing you declare them all first and then give all the definitions afterwards. So had to move the declaration of cons before the definition of list. So it's not entirely a bed of roses, but it's not too bad. And finally, there's a bit of noise with going from an element of an ordinary aggregate type set that's not intended to be a domain to a domain and then injecting it in the sum. And that's where we exploit these injections between the summans and the sums. But AGDA would require that injection to be made explicit anyway. The eta there is the thing that takes an element of an ordinary set and gives you an element of a corresponding lifted domain. Now to the well-formedness issues, getting near the end. I can't give you a definition of what well-formedness is for denotational semantics. It's a mathematical notation. It's not precisely defined. So I'm going to show you some examples that you may or may not agree with. I'm not sure whether this is a well-formedness issue or not. It's overloading in the scheme standard. False and true are declared in two different domains. And when you look at the definition of truish, then you may get a bit confused about which domain you're talking about. And in fact, there's also another bug in that definition. You're not allowed actually to test whether an element of the expressed values is equal to something else because that is a higher order domain, and you can't have a continuous equality test on a higher order domain. So really you should project the epsilon that stands for the a value in scheme onto the domain of miscellaneous values M, and then test in that domain, which is a flat domain and has a continuous monotonic equality test. So there are a couple of issues there. Ironically, there's also an issue with the definition of the auxiliary function that's called wrong, which I found a delightful irony. Wrong is used all over the place, applied to strings. And that's the type of wrong. And that's not compatible, at least Agda doesn't think it's compatible with leaving X unspecified. X is not guaranteed to include strings. So I think that's really a genuine well-formedness issue. When I was about to submit the paper for the workshop, I was thinking maybe I'll just manage with the auxiliary functions that were actually used in the semantic functions and leave out the ones that corresponded to standard procedures, in particular this call with values. But then I had a bit of time before submission deadline and spent a couple of hours converting the scraped Unicode characters from the PDF into Agda and inserting the spaces and getting it type checked. And to my delight, the very last one I checked had a bug. Do you see what the bug is? Many people have probably looked at this and ignored the fact that the kappa argument is simply ignored and thrown away. There's a typo that was, it should have been added as an extra argument in the highlighted part there. So this shallow embedding idea has some utility, let's put it that way. There are some more obvious problems with well-formedness. In particular, the compositionality is abused. Both of these, the second one is rather innocent, you just expand it out. The first one is really serious. You can get around it, there's a suggestion in the paper for how to do that. I'm not going to go into that here. The final thing I'd like to say is that, let me just put up that penultimate slide completely, that the definitions in continuation passing style sometimes start using stores, mixing direct style and continuation passing style, which is extremely messy. You can redefine this cons auxiliary function very concisely using continuation passing style, and it looks much nicer, and that's the way it is. So my final slide, conclusion, we have a shallow embedding. It reports those issues that I've mentioned, and there's an artifact that you can look at if you like. I hope you will. And it would also be very easy to update that 5th revision to the 7th revision and fix the bugs there. And what I'd like to know from this community is if there's any interest in continuing to have a denotational semantics in Agda. And anyway, thank you for your attention so far.
Any question here? Oh, lots of questions.
So speaking as an editor for R7R Small, I'd like to apologize for our job in denotational semantics and also recruit volunteers for R7R Large.
Yeah, thank you. Thank you for the question. That's a very good question. So for scheme, I've only done very little in proving denotations are sound in relation to what you expect to be the results of running the programs that you expect, that running 2 + 2 gives you 4 and things like that. For simpler languages, I have 3 examples that you can find if you follow my if you follow the links from this topic on my webpage, there's the pure untyped lambda calculus with the D-infinity model. There's Plotkin's PCF language, and there's the SCM language that's from this paper. That's the simple basic language that are on the website. For the untyped lambda calculus and for PCF, I do have examples of where the using the embedding, you prove various equivalences between denotations, and as far as I can see, that's the proofs are just REFL in Agda. You don't have to spell out the proof. The trick is to add some equations as rewrite rules. Agda allows that. By the way, that's a good reason not to use module parameters, because module parameters can't be used as rewrite rules. Postulates can. When we have, for instance, in the model of the untyped lambda calculus with D-infinity and an isomorphism or bijection between D-infinity and the function type on D-infinity, then when we get pairs of compositions of those two parts of the isomorphism in the denotation, we want to carry on the computation by eliminating the bijection going backwards and forwards between D-infinity and its function type. And with that rewrite rule in Agda, then you can do quite a lot of computation. But in general, it's rather skating on thin ice to be using potentially unsound postulates as rewrite rules in Agda. But so far, so good. Thank you for the question.
And maybe last question, just. Okay, maybe another one. I see some frantic waving.
This is short. There's not even a question mark at the end. There is every so often discussion on the R7RS small mailing list about nits here and there that might not actually be quite right and need to be. So my short answer is yes.
Okay. So in any case, I must admit I haven't been. I browsed a bit one of the mailing lists, which led me to the work of Anton van Straten with an executable version of the scheme semantics that was written in 2001. The website had disappeared, but I managed to retrieve it from the web archive. And interestingly enough, I found as a comment in his code, in his scheme code, I found a comment that he'd also noticed this bug in the definition of call with values, CWV, and I hadn't looked at his work before I'd found it using Agda, but it was nice to get confirmation that I was curious if he had a valid implementation of scheme, why hadn't he found that himself? So he found that in 2001. I'm not sure it was ever reported or discussed on the mailing list, but it was only the mailing list that led me to his work.
Well, thank you for lifting it from commenting code.
Thanks, Peter. Great talk, obviously. It's great that you wrote that paper, but the perception of denotational semantics seems to depend on the person who is talking about it. If we look at like Dave Schmidt or Glenn Winskall or Samson Abramsky or this kind of guys, they say denotational semantics is really about domain theory. And boom, then we are started with the way domains are constructed and the way the mapping from domain to domain is continuous or not. And so there is tons and tons and tons of work about that, which you just say, oh, just consider domains as types. And an example of that is when I was reading your other paper on, I had a question. I thought there was a typo. Then you told me, no, the bottom is implicit in the domain. You didn't explicitly lift the domain, so it is okay as is. So that's something that I clearly still don't understand. So the saying that the domain is just a type and then you can happily go and write, that exactly corresponds to the original semantics of scheme, which was machine implemented and then mapped into LaTeX. Yeah. So that means that the original semantics of scheme was ostensibly denotational because it was formatted in LaTeX, but there was no domain content, except that Will is an expert in domain theory. He did his PhD thesis with power domains, non-determinism, and that kind of things.
Okay.
So I still have a
let
huge
me answer a bit
question
of that
now.
to start
Yes,
with, before you continue.
I was done.
So, yeah, basically, what I'm doing is parametric regarding all the different flavors of exactly what domains are. If I'm going to reason about loops and recursion, then I should probably need to use Kleene sequences or limits of chains, at least, of approximations, and the approximation order will need to be explicit in the reasoning. So postulating also the order and its properties will be part of the postulates. The second thing I'd like to say is that in 1980, Dana Scott had a proposal for synthetic domain theory, which was getting away from all this classic set theoretic construction of domains as CPOs with particular carrier sets and partial order relations and completeness properties, which if you represent it in AGDA, as in the type topology library, where you find very carefully developed definitions of domains, there you have a lot of work to do with continuity proofs all over the place. Now, Scott's idea in synthetic domain theory was that in constructive logic, you can get away with assuming that all functions are continuous and therefore have fixed points, and that all types are domains. Now, that's not compatible with AGDA as it stands, because not all types need to have bottom elements. But if we can at least find some middle ground where we can go away from these blatantly unsound postulates and end up with postulates that correspond to a version of synthetic domain theory supporting both domains and so-called predomains, which are domains that don't need to have a bottom element, that could be an ideal way of getting a sound version of what I'm doing implemented in AGDA. And that's my next project before I really retire.
May you never retire. But still a last point in my paper, in your Festschrift, there was a facetious paragraph about the jungle of semantics of scheme. And I was listing 15 papers that were specifying call-CC, all in different ways. And the question was, in all this jungle of semantic artifacts, which one is the real call-CC? And then I proceeded to interderive all these semantics, which made some enormous assumptions about simplifying. But then I could touch all the semantics. And then there was not, here is my semantics, and that's the semantics of scheme, and here is your semantics, and your semantics of scheme, and which one is the semantics of scheme? When do we know? And like full abstraction, Allah. Okay. Is there a full abstraction between the denotational semantics of scheme and the published operational semantics?
I've never subscribed to the doctrine that you should go for fully abstract semantics. It becomes so complicated, and the intention of denotational semantics, in my view, is to express the intended understanding in terms of representation of programs in terms of pure mathematical objects, values, without invoking an abstract machine. Strachey all the time was objecting to Landin's approach, where Landin had an abstract machine in the background to evaluate his lambda expressions.
Mm-hmm.
Strachey wanted pure lambdas, and from the beginning of the 60s was working on that. And I think that what I hope I'm doing is essentially making Strachey's original vision viable in AGDA.
And that's super honorable. However, if we take Landin's operational
semantics... I'm sorry. Why don't you all take this to the coffee break?
Fair enough.
I think some of us, need to get going. But thank you very much. Let's thank Peter again.
Thank you. Thank you for your leniency.
Because what you're doing is turning it into software, so now we can apply software and ideas, like your example with the log. So, is there any appetite upstream for this? Like, is it something you could maybe change in the spec, or is that so?
Hi everyone, welcome to the last session of the scheme workshop. So the first talk of this session is an invited report from Daphne. And it's a remote talk.
Hello. 1, 2, 3. Please respond, over.
Yeah.
Hello?
Hello? Hello? Yeah.
You hear me?
Yes.
Excellent.
We hear you.
Okay. Everyone still hear me?
Yes.
Excellent. So, good afternoon to all of you in Singapore. Sorry I can't be there in person. Before I get on to the original planned content of my talk, events rather got ahead of me, and how I had originally planned to use my time here. Plans have had to change a bit, but I have an important announcement, and then there's a slightly compressed version of what I had originally planned to say. So the big announcement is that we are holding a new election to the scheme steering committee. The process for this will start now. In order to avoid important election dates falling during the winter holiday season, we're going to have a very long, or fairly long, registration and nomination period, and then there will be a result in February. So the first question you may ask is, why are we doing this? The working group that I chair asked for a new steering committee because the current outgoing steering committee had essentially got out of practice at being a steering committee. It fell dormant for a very long time and was no longer able to meet regularly and make the decisions that we as a working group really needed from it. If you know Scheme, there's probably some names you recognise here among people who've been on the steering committee so far. Guy Steele was on the first one with Borden and Wand. Steele invented Scheme with Sussman. Feely created Gambit. Klinger edited the reports between the R2RS and the R5RS and quite a bit of R6RS. This current steering committee with Feely, Rees, Klinger, Hansen, and Shivers started in 2009, oversaw the R7 small report, but after that was ratified, sort of, as mentioned, fell dormant until my predecessor as chair of the working group, John Cowan, resigned, and they had to become active, and for some reason they appointed me in his place. So for 2026 onwards, we will have a new one. What is the steering committee? The steering committee sets the ground rules for us as the working group. It decides roughly what the report would look like, sets some basic requirements and goals. They give me advice and indirectly the rest of the working group advice. They appointed me, as mentioned, and they can dismiss me. They enforce the code of conduct of the working group. They run and own some of the digital infrastructure that we as schemers depend on as a community. They organise the ratification of the report when the working group is done. And when the working group is done, perhaps most importantly, they decide what happens next. When my job is done, when R7 Large is done and dusted, they will still be around and they will decide how to continue. So, to find out more, to register to vote and to nominate candidates, you can go to this address. It's r7rs.org/sc. That's r7rs.org/s for steering, C for committee. As mentioned, voter registration and nominations are open now until the 15th of January. We will have voting in the first 2 weeks of January, and then there will be a result shortly thereafter. Okay, so important announcement out of the way. Now to, as promised, the slightly compressed, originally planned content of my talk. My name is Daphne Preston Kendall. I am, as mentioned, the chair of the working group, which has been entrusted with the next revision of the scheme report. And I would like to deal with the question in this talk of what does a good scheme report look like in 2025? How is it different from maybe 1975 or other times when people have been making the scheme report. And I would also like to invite you all and the scheme community as a whole to a discussion about these questions and see if you think I'm right or not. So as creators of the scheme report, like creators of any text, we need to ask, who are we creating it for? We need to think in terms of a real audience. Who are they? Who are they? How are they using scheme? How are they using the specification? And what do they want? And what do they need in order to do their thing? So you can think in terms of vague constituencies. These are never going to be like any grouping of a diverse, like any subgrouping of a diverse group, like all schemas. Not everyone in every constituency will always think the same, but a very basic one is implementers who want something they can actually write a good compiler for, versus users who quite often just want their pet features added. So there's different pressures there. But in some cases, the interests of implementers and users are aligned, like in embedded use, where both sides really want a small memory use and suitability for resource-limited environments. Another pair of constituencies that are kind of in tension with one another is users in education. You can read the papers about the creation of the textbook How to Design Programs for very interesting reports on the specific needs of a student, of a good student language. And on the other hand, there's those who have been scheming for a very long time, which these days is mostly hobbyists, but also some professionals. With Scheme, though, often we are thinking about more explicitly political constituencies in the sense not of the political parties that we have in our everyday politics, but different ideas of what Scheme is as a language, different ideas of what Scheme should become based on the idea of what is its essential essence. Here's one constituency. The idea that the R6RS and our work on the R7RS large language is a kind of a goal to create a big scheme against a little scheme party is one that is sometimes being accused by others of kind of sacrificing this smaller nature. You find this kind of wording, a diamond-like jewel, in lots of places, criticizing the R6RS, criticizing us, the R7 large working group. This particular formulation of words is from Dick Gabriel's Worse is Better essay, which is probably where the metaphor originated. And it seems that just as physics and geochemistry put limits on how big a diamond can be, and our aesthetics as humans limit how big we can make it as jewelry, just in that way, it seems from the objections to the R6RS and to the objections to what we're doing, that there may be limits to how big Scheme can get and still be this diamond-like jewel. On the subject of this kind of big and small language tension, I would like to call back to Guy Steele's 1998 OOPSLA talk, Growing a Language. If you don't know it, I very much recommend reading it or listening to it. But he actually talks about Scheme in this talk. And I would just like to read briefly what he says. He asks, could not the right thing be a small language, not hard to port, but with no warts? I guess it could be done, but I, for one, am not that smart, or have not had that much luck. But in fact, I think it cannot be done. 5 and 20 years ago, when users did not want that much from a programming language, one could try. Scheme was my best shot at it. But users will not now, with glad cries, glom onto a language that gives them no more than what Scheme or Pascal gave them. So there is a reason, if you're not familiar with this paper, there's a reason for a slightly strange mode of expression there. But he's talking about how user expectations, user requirements from a language have grown over time. And in particular, in 1998, he talked about wanting to make graphical interfaces, to do networking and talk to remote APIs, to hot load code into a running program, to do multi-threading, multi-processing, and have distributed systems, and to have multilingual text. From these, one notices very much that Steele was talking about Java in 1998. Some of these things are now out of fashion. Some were thought of as good ideas at the time, but are now seen as bad ideas. Some of them never caught on. But some are just as important as ever. But even those which are as important as ever, sometimes no longer seem like things that a language should have to take care of, but rather the province of third-party libraries. Indeed, Steele actually concludes growing a language in favor of letting users grow a language by libraries. But he says a too minimal base, like that of 1975 scheme or even 1998 scheme, is not enough. Now, originally I had planned a little audience participation round here, but I don't have time after the announcement, so I will just simply summarize my own answer, which is both yes and no. That Steele is basically right that growing a language is good, but that scheme in 1975 lacked important features. What people object to is generally not bigness per se, but where the bigness comes from. If they make the language big themselves, very few object to this. If the report itself is 1,000 pages long, this tends to be a cause for concern in some quarters. Our disagreements are over how to grow the language, not over that it should be grown or growable. What about another political division? I want to talk about another paper called The Structure of Programming Language Revolution, also by Dick Gabriel. Gabriel talks about taking a break from programming languages in the early 90s to do a fine arts degree. When he returned in the late 90s, the scene had completely changed. People used to talk about dynamic evolving systems like Common Lisp and Smalltalk. But by the end of the 1990s, they were talking about static languages like Haskell. I hypothesized that the scheme world lived through this transition, but without really noticing it as a community. This is one of the reasons for the divisions which arose immediately after this paradigm shift. Some members of the community adopted the new paradigm, and others preferred to stay with the old. And the two sides fundamentally do not understand one another and each other's concerns. The dynamic systems approach is epitomized by the R5RS, which only has an interactive top level. It even added the beginnings of a namespace system that was based on first-class environments and the eval procedure. Implementations which follow this model include Guile and MIT Scheme. The static languages approach, on the other hand, is epitomized by the R6RS, which has no standard interactive top level. Its implementations include Racket, Loco, and Shea Scheme, but also, in the most extreme cases, niche implementations which have no interactive mode at all. Put briefly, dynamic languages people see Scheme simply as a dynamic language. The static languages people see Scheme as a static language in all regards except for its type system. This appears to be a fundamental difference in beliefs about which primitives to use, what Scheme fundamentally is as a language, and therefore what the right abstractions to build are, and how the Scheme report should look in the future. So I've mentioned just two kind of dimensions of disagreement here, but already if I plot them on a table, and compare similar languages that people might like to use as models for what Scheme should be like in the future, we see a huge range of expectations. Except for maybe Lua, I've seen appeals to all of the languages that are on screen now as examples for how schemes should be in the future. Lua, those who want a little dynamic language tend to appeal to earlier versions of the report rather than to another language. And these, I emphasize again, are only two dimensions of disagreement. I could add even more axes for philosophical agreements, for even more of them, disagreements about procedure, how we should make the report, and even more for individual specific features. Given all of these divisions that seem to be so fundamental, one natural question is whether it still makes sense to make a scheme report. And one possible answer is no. Some already answered during the R6RS days and in the R7 small days that scheme standardization would stop. So just as Racket has no longer claims to be a scheme report implementation in its default mode, other schemes would slowly diverge from the report and from one another. Guile would no longer be Guile Scheme one day, but simply Guile. Chicken Scheme would simply be Chicken. Like the many descendants of Algol 60 and 68, and the many dialects of those descendants, the languages would eventually evolve to have a common ancestor, strongly recognizable in each of them, but each distinct and, importantly, incompatible. It shouldn't surprise you that I do not think that this is the way to go. I still want to be able to solve the problems I perceive in the common base of all of these languages, and I want to make my solutions available to as many schemers as possible in one go. And I emphasize that I want to do this as a user of Scheme, not as a committee member. I want to do it through libraries, not by creating a 1,000-page Scheme report. Bracket is also an excellent example of the problems that could arise if we were to abandon standardization. Racket has some great features, but they are not available to other users of other implementations because Racket's own implementations of them are not portable. The same problem applies even in implementations which haven't gone quite as far as Racket. Guile users use Guile's own implementation-specific module declaration, so their code is often unavailable on other implementations. There's a lot of Guile code out there which I want to use on Shea or Chibi, but porting work is required even if the actual code content of the library only uses standard scheme features. If you notice then that this is more or less the same rationale for scheme reports that there has always been, and I believe it still applies. The question then is reunifying not only implementations, but also the reports which have become emblematic of the splits in our community. While to some extent the R6RS editors and community are justified in feeling that R7RS Small abandoned their work, in fact, in many respects, the R7 Small report vindicates the R6RS's decisions. This is because the committee, although they may have set out in another direction, fumbled their way to an important realization, which I'll get to in the next slide. The idea that R7 vindicates R6 may seem like a shocking claim about this division, since many have said it would threaten to kill our community. Fundamentally, though, both reports versions agree on a static semantic for libraries. R7 library declarations, although they involve conditional compilation and other features not supported by R6, define basically the same model. It is true enough that these complex R7 library declarations can be compiled ahead of time to R6 ones, and in fact there is already a program which does this, Aku. R7 Small also adopts many of the criticized features of the R6RS, byte vectors for binary data, Unicode for strings. Can you believe that people really resisted that 18 years ago? And has the same exception raising and handling mechanism. The realization that the R7 Small committee fumbled its way towards is that the report is a minimum and not a maximum for implementations. Just because the report is small does not mean that an implementation cannot be big. Just because the report is static does not mean that an implementation cannot be dynamic. The small and large report split helps even more by setting two different minimums according to different requirements of implementations. Moreover, the practical needs of programmers have evolved over time, such that little and big mean different things than they did 25 years ago. Byte vectors were likely uncontroversial in R7RS Small because by the time it came out, programmers had become used to their appearance in languages such as Python 3 and JavaScript. Unicode likewise. There is also culturally much wider acceptance now among programmers of the need for safety, another controversial feature of the R6RS. So this is my appeal to the scheme community. If we do not have a report in which the vast majority of implementers and users will tolerate, Scheme will simply die as if we had no report at all. Not all of the implementations on screen would die, and I would probably guess which ones would and wouldn't survive, but even those which did survive would be weaker for being unable to take advantage of libraries written for the others. But, I emphasize, joining means compromising. Nobody will look at any Scheme report and say that it is perfect. Even if it were a perfect diamond-like jewel for one person, it can't be all things to all people. Perfection means different things to different people. Scheme has historically been too shy of compromise. This uncompromising pursuit of perfection, even though nobody will ever agree on it, it may be why we have struggled so much to move onwards as a community, while other languages have not. To that end, I would just like to quote my predecessor John Cowan. This is something he said when he voted in favor of R6RS ratification. He said that a well-crafted compromise is, in my opinion, the most sacred thing that a secular age knows. If we cannot have a diamond-like jewel, we can at least have something. We can at least have the most sacred thing that a secular age knows. Well, that concludes the philosophical part of my talk. I would just like to move briefly now to the progress report that I think most of you probably more expected. We are working on the R7RS large foundations, that is the core semantics. The procedural fascicle will be out in a few weeks, I hope. Or it's called procedural, but it's mostly syntax, but for procedural programming. So things like lambda, let, and con, and so on. As you can imagine, it will be a fairly conservative extension of what we've already had in previous Scheme reports. And there will also be a second draft of the previous article, which I expect will mostly be minor editorial fixes. There may be some small technical changes, but I don't expect so. If you want to find out more, if you want to find out what we're thinking about a specific issue, you can go to our repository and issue tracker. You can give us your feedback on an issue that's important to you, and you can even join the working group. We're still welcoming new members, and we meet once every fortnight, every 2 weeks. And just to finish up, for anyone who may have entered the session late, I would just like to finish with another short notice about the election. We are holding an election to the Scheme Steering Committee. You can find out more at this web address. And if you have any questions for me, if you want to tell me how right I am, how wrong I am, give your opinion on how the scheme report should look, I am on the Discord. Arthur Gleckler should be in the room and should be able to take questions about R7RS progress and about the election as well. Thank you very much.
Thank you, Daphne. So, shall we take?
I don't believe we have time for live questions.
Oh, but we do need to like switch. Yeah, you can connect and then while doing that.
Do we have time for questions? Oh, okay. So this is a question really from outside the scheme community.
Okay.
Building a standard like R7RS is a lot of work, and that's what you've been reflecting. And so my question, in terms of the cycles the community spends, what do you think the sort of cost-benefit trade-off is? And I ask because in the Haskell community, essentially, what it amounts to is we've given up, right? We no longer produce a new report about Haskell every few years because it's just been too much work and nobody's been willing to sign up for it. But somehow you guys have continued to invest that effort. I'm just interested in the sort of the costs that you incur and benefits you think you get from it.
Well, I think the main difference between Scheme and Haskell in this regard is that Scheme is still a language of very many implementations. There is still, and I personally hope there will never be an implementation as dominant as GHC is in Haskell. That's not to say that GHC's model or Haskell's model is bad. I think it works very well for you, and I think our model works very well for us. In terms of the cost, I mean, as mentioned, we've had these very significant divisions in the Scheme community about what our report should look like, and that has been reflected in different philosophies that implementations have taken, different implementation strategies. Some have argued that we should give up on ahead of time compilation entirely and go to features that would essentially require the adaptive optimization of a JIT in order to implement efficiently. And more or less the Scheme report has sort of stayed more towards the ahead of time implementation of that, specifically because you can use these static semantics, as I mentioned, can be incorporated into a dynamic context, but not the other way around. I think I may have got a little off topic at the end there. Have I answered your question?
Good. Thank you so much.
Is there any other question, or are we moving on to the next talk?
Right. Let's switch to the second speaker.
Okay. Thank you very much.
Thank you. So our second talk is about verifying a compiler for Scheme, and the talk is given by Pascal. Yeah, please.
Compiler that we built called BRAC. The name BRAC is supposed to be short for barn brack, which is a kind of Irish fruitcake, which fits into the theme of cake-based compiler names in the KML ecosystem. Which Jeremy came up with that name because he's quite good at making names for things. So, just a quick summary of the whole thing. BRAC is a verified Scheme compiler. It's written in Whole4, the Whole4 proof system, which is the same as what is KML is written, and the reason for that is because we're building on top of KML by targeting that ML, and we compose our semantic preservation proofs, which I'll explain in a second. To our knowledge, it's the first verified compiler which supports dynamic typing and first-class continuations, and it compiles using a continuation passing style transform, and I'll explain kind of the motivation for that. And so, firstly, just to quickly explain what verified compilation is to those who may not know. You're implementing the compiler in a proof assistant, and then what that allows you to do is if you have the compiler definition and the semantics defined within the proof assistant, you can use those together to construct a semantic preservation proof. And this is roughly the shape of that sort of proof, which I've left deliberately vague because the specification is kind of flexible. At a top level, what you want is to have the observable trace of execution of a program to be conserved from the source semantics to the target semantics. And then kind of at a more specific level, which this diagram sort of represents, like in the case of our semantic preservation proof is a simulation proof for Scheme. You'd have reductions. This basically is supposed to say the reductions in the source and target semantics should be the same before and after compilation. And I've also left those squiggly arrows to be a bit ambiguous because that can either be actually the compiler or it can be a relation that the compiler satisfies, and then you make sure that square commutes. And then an important part is that you can compose these semantic preservation theorems, which is exactly what we do by composing our semantic preservation proof from Scheme to ML with KML's existing proof from ML all the way down to machine code, and that's how we get a complete verified compiler. And so this is not, in light of the last talk, this is not a political choice. Our BRAC is based on the formal operational semantics from the 6th report. There's not really much of a particular reason for that. The reason why I chose it, I think, is because it was easier to kind of extract like a subset, the small subset that we wanted to target from the 6th with the operational semantics rather than the denotational semantics. And this basically is a subset. It's not very big. Importantly, it has lambdas and call CC and lists, so you can express some interesting list like data processing operations, immutable lists, but lists nonetheless. And BRAC forms a single compiler pass from Scheme to KML, which involves a continuation passing style transform. And kind of the point of all of this is that the naturality of the CPS transform is what makes the semantic preservation proof kind of, in a way, easy to do. And this is no coincidence. You can effectively arrive at the CPS transform directly from the specification of the small step semantics. This really came from Danvi's work on refunctionalization. We use that idea to take a CEK machine or CESK machine to arrive at effectively a CPS definitional interpreter. And what you end up doing is, if you think kind of like partially evaluating that over a program, and then you end up with an AST, and that, in a sense, is a compiler. It's not a very efficient compiler, granted, but it is easy to prove, and that's kind of the purpose of this work. And yeah, so basically, with that line, it becomes, semantic preservation becomes a matter of proof of correctness of refunctionalization, and then proof that that partial evaluation kind of embedding into ML is also reasonable. And so I want to give a tiny example of what that kind of looks like. I especially want to kind of, yeah?
You said the neutrality of CPS makes the proof easy.
Yeah.
Is it because it's compositional, so you can just do a proof by induction?
It's not even by induction. We just do it because we only do like a simulation proof for each step, and then we can just do a case match over all of the steps. And so I'm going to give a kind of example of what this refunctionalization looks like, which I'm sure a lot of people are probably familiar with, but I'm explicitly adding assignment and mutability into this example just to kind of show how, as you start to add different language features, how you can adapt the refunctionalization technique to a language. And I've chosen to use a CESK machine. It works really nicely with refunctionalization. Mostly existing KML in ecosystem uses this style of small step semantics. So we're following on with that. And lambdas don't take lists. They just take a single parameter. So you could probably, this is basically just like a call by value lambda calculus with mutability and assignment. And so this is what the CESK machine looks like. I hope this is not too surprising to anyone. it's the call by value lambda calculus, but instead, when you continue with an application, rather than just binding in an environment to a variable, you bind to a fresh store location. And so that is how you can then use mutability. And then set is the expression where here you change the value in the store. And so refunctionalizing this, you'd end up with a CPS definitional interpreter, which looks a bit like this, which again looks quite similar to the call by value lambda calculus one, but we're instead using a store and doing fresh allocations. And so what you can then do is this is the same definition basically, but I've just shifted things into some lambda abstractions. And then I'm going to color it pink, just to make the difference to say this is no longer like the defining meta language that we're using to define the interpreter. We're now saying this is ML, we're compiling to this is an AST, and then, the blue is the scheme, the pink is the ML, and then the black is the defining meta language. This is not actually, and this is basically what I mean by we're doing it like a partial evaluation over the scheme program. We want to expand it fully over the scheme program, and you can't actually do it right now with how we've just directly done it. Maybe you might be able to see why. The reason why is because when we try to expand over this expression doesn't actually exist yet because we bind it inside of a continuation closure. So this isn't actually a compiler yet. Turning it into a compiler is a matter of moving that transform up into the definition of the lambda expression itself. So that should look familiar. And then this is basically a compiler, but it's quite bad because we have the simulated environment and store we're carrying around, which is redundant. And the reason why is because now that we're in ML, we actually have access to refs. So we can do mutability basically directly with direct compilation. So the first thing you can do is get rid of the store, and you have a slightly less bad compiler where instead of doing the fresh location allocation manually, we're just using the ref syntax, and that does everything automatically. You have to dereference variables, and then assignment basically comes very easily where you just sequence an assignment from ML. And then you can get rid of the environment, which is a case of scheme and ML share the same lexical scoping, so you just use variables directly in ML. And then you arrive at basically the Plotkin-style CPS transform with the slight difference of you're using references to enable mutability. And this is just like an example with a very small scheme with mutability, and I hope to convince you that this technique scales, and you can apply it to a larger scheme, like the scheme that BRAC supports. You can use it to compile control operators like call CC in the continuation passing style, and with all of that, you still get the same benefits, basically, of the simulation proof, and semantic preservation proof becomes, relatively speaking, quite easy to do because of the naturality of this derivation. And so, to summarize, BRAC is a complete verified compiler for scheme, and that subset includes call CC. And we use refunctionalization to derive this CPS transform, which is effectively correct by construction from the semantics directly, and we can apply this to a larger language from this example, and that includes call CC, which ends up actually, funnily, either surprisingly or not surprisingly, is the easiest part of the compiler to prove. And so yeah, that's made simple. So thank you very much.
Thank you.
Thanks, great talk. I understand what you did. Can you backtrack to the point where you introduced the store? Yeah, so if you were putting the store last, then you could eta reduce the store, and then it would kind of disappear. And then the only place where you need it would be, since it's all tail calls, it's almost like a monad, a state monad, where everything is implicitly eta reduced,
right,
and you need one operation. So there's no need to be as explicit as you did. Okay. If you put the store last, because then you can eta reduce it, and now you have something in CPS.
Okay.
So there is nothing to invent there.
Okay,
and the proof should just small things to change.
Well, one thing I should clarify is that we don't, like, this definitional interpreter doesn't actually exist within our proof, basically. I'm using it more as an example of showing how you arrive at the final Like these are mental steps that you take.
Okay.
But because of the way that you can arrive at it through this process, you can be confident basically that you can do the simulation proof and it will work. This is often just the issue with trying to verify something is if you just make a compiler and then you verify it and you're like, I don't know if this works actually, and then eventually you find something wrong with it. Making sure that you derive it from this sort of system means that you can be sure that as you're verifying it, as much work as that still is, it's still laborious, you can be confident that it will work. And if it doesn't, you did the derivation wrong and you need to fix it.
Okay, that totally makes sense. But if you swap the sigma and the kappa at the top, it gives you lambda, rho, kappa, sigma, and then you can eta reduce the sigma, except for the operator that needs it.
Okay,
and so the sigma goes away from everywhere, it disappears. Which is, as Peter Moses was saying in his talk, is also used in the semantics of scheme, where there are lots of things that are not there because it's carried and eta reduced.
Oh, I see. Like the denotational semantics?
Yeah, for example.
Okay, I'll need to take a closer look. Okay, thank you.
All right, thank you very much.
Hello, yes. I'm going to be talking about Minidusa, an extensible finite choice logic programming language. I'm Ari. This is joint work with Zach, who is here. Yes, so if you want to talk about Minidusa, we should first talk about what Dusa is. Dusa is another logic programming language like Datalog. Programs consist of facts and rules that you can use to deduce more facts until you can't deduce anymore. We're going to talk, as an example, you can consider this graph. This graph you can encode as a bunch of facts that look something like this, and you can say that an edge from x to y is the same as an edge from y to x to ensure that the graph is undirected. And if you want to look at graph reachability, you can define a reachability relation that says that if you have an edge from x to y, it's the same as having, you can reach from x to y, and if you can reach some node and you have an edge from a node to another node, you can reach that one too. Then we wrap this in a logic block and run it into our solver, which gives us a solution that has some facts in it, and this will look like a series of facts that says that you can reach from A to B, A to C, etc. One thing that Dusa adds on top of the data log-like semantics is finite choice, where you can describe mutually exclusive choices between several values, where you can get several solutions that each reflect different choices that were made. If you look at this graph, you can have a relation color that takes a node and assigns it a color that is red, green, or blue. And this will give us a solution that looks like this, where you can see a color is effectively a function that maps a node to a color. And if you want to look at this graphically, you will get a graph like this. And you can get another solution that might look like this or like this, which is not a very interesting computation because this will compute all 3 to the 5th possible colorings of this graph. And we want to forbid the ones that aren't valid. So using the forbid rule, we can say that if there's an edge from x to y, we forbid that they have the same color, which will throw out that solution and get only the ones that are proper colorings. So these are all the features of Dusa, and we want to talk about what we added on top of this. So we will talk about the implementation of Minidusa. We implemented Minidusa using syntax spec, which is a meta language in Racket for defining extensible DSLs. You define the language grammar and the binding structure, and from that you get macro extensible DSL, IDE support, and interoperability features with Racket for free. And the way that we use syntax spec is that we specify our grammar, and that expands our source syntax into a core where we can do static checks on it, and then call our runtime functions that give users our solutions. So as we talked about, we have macro extensibility, which you can use to take a graph that might be complicated to describe and express it using a more familiar syntax for people, like an adjacency list. This is just a syntax parse macro that you can implement using any normal macro, like scheme macro. Macros also allow us to abstract over encodings, so you can go into the implementation of this macro and change what it does, and you can use that for hiding implementation details and making things more efficient. And one cool thing that we get from the macro system is that we can implement the demand rule that we saw earlier as a macro. The macro just deduces a contradiction if the premises that we provided are met, and that causes the solver to throw out that solution. One thing to note here is that every use of the forbid macro will make a fresh relation called OK that doesn't conflict with any of the other ones that were previously defined. DUSA hard codes these into their solver, and we don't have to do that, and we can just define them on top of our core language. Another thing that we get from syntax spec is that we can import functionality from Racket, and we do this in terms of the import keyword. We can import a function that might be doing something like, if you have facts about people and you want to do something with dates, doing date parsing in logic programming is really hard, but in Racket it's really easy. You can just define this function, and you can use it inside miniDUSA as if it were just a functional relation that we defined. And this ensures that you can do the thing that is easier to do in either of the languages, and you can interoperate between them. And on the other hand, when we have functions, you might want to also import data from Racket, and we can also do that. You specify that you want the person relation to come from outside, and when you call the program, when you call the solver, you provided some facts. This can be fetched from the internet, from a database, whatever, and you're effectively operating on external data using external functions and using miniDUSA as a subroutine, which means you can use language-oriented programming where you can work on problems that are easier to express in Racket, and easier to express in logic programming in miniDUSA, and freely choose the right tool for the job. And we have several other features that we had to cut for time, like open rules for optional choices, demand that is the opposite of forbid, where you can require that solutions match several constraints, imports for macros to use within their local bodies, and several in-progress features like Racket APIs that are easier to use, etc. Yeah, that is the talk.
Thank you. Any questions? No? Could you go back to the previous slide?
Mm-hmm.
So I would like to, oh no, the future work.
Oh, yes.
Yeah, I would like to hear more about what the improved Racket API means.
Currently, we have we haven't done a lot of work into the API part of this. We have a function that will give you a stream of solutions, and it's kind of on the user to search for what they're looking for. And it would be easier if you can describe the shape of a fact and you can be like, I want to check, for example, that you can query the specific color of a specific node or something like that, which you would have to do manually otherwise.
Okay, thank you. Any other? Yes.
What is the actual implementation of Minidusa look like? Are you using kind of a traditional naive data log evaluation procedure? Are you using like a magic sets kind of optimization? Or is it somewhere in between?
Yes, that is the mini part of Minidusa. It is an extremely naive solver.
Great, thank you.
Hi, I was wondering, why do you end up having to use the import form rather than just having if it's a racket binding, it's just magically available?
This is the way that syntax spec operates. We want to define a specific class of variables that are available to use inside our logic block. And if you want to like bridge across to the racket world, you have to have some kind of form that defines them.
Okay, you didn't just want to everything is available because that would, okay, thanks.
Good. So, thank you. Now, it's time for our keynote.
So I will introduce you while you set up, okay? The Scheme programming language was integral to Michael's education. He earned a PhD in computer science at Indiana University under the direction of Ken Dybvig, and he has worked with him on Scheme. He has worked with Simon Peyton-Jones on the implementation of GFC. He has been very active about anything functional. He has done noted work about parser combinator with MatMite. And after a number of years of postdocs, he joined Yale NUS College exactly at the time where Yale NUS was announced to close. So he switched to the School of Computing, where he's hailing us from today. He has been active in the Scheme community, have been served in the Scheme workshop for twice, and he has chaired the workshop in 2020. And today, he's going to tell us about his idea for future research directions in Scheme.
Thank you. Thank you very much for that. Okay, so it's wonderful to be here. And as Olivier said, I want to share with you some more speculative ideas about future directions for research that could happen in Scheme. And I do want to emphasize, this is very speculative. And second, I hope you steal these ideas. I place no claim on these ideas. I'm presenting it to you because these are ideas that I think need multiple different people exploring in different directions. And as it has been said sometimes, Scheme community can be a little bit like herding cats. Well, for these ideas, that's a good thing because there's a lot of territory to explore. Okay, to start, I want to give you a little bit of perspective of where I'm coming from. So a lot of my research comes down to the concept of improving programming language ergonomics and exploring, improving programming language ergonomics. And the fundamental problem is that when I write code, I have some image in my head, but so often the language I'm working with slows me down. Now, some languages slow me down a lot. I'm going to blame certain languages like Java. Other languages slow me down less, such as Scheme, but they still slow me down a little bit. So I want to find those places and improve on them. This leads to applications in a number of areas. This includes applying techniques that will improve domain-specific languages. Because the particular task that you're working with, it's useful if you use a tool that's tuned to that task. This applies to things like metaprogramming and generic programming and macro hygiene in order to be able to write these domain-specific tasks. Macro hygiene is actually rather interesting because there's an ergonomics at two different levels. One is I want to make the process of writing macros easy. And two is I want to make sure that when someone uses the macros, that they can trust that the macros aren't going to do weird things. This also applies to areas such as parsing, static analysis. This also applies to areas of parsing and improving because notation ends up mattering. This also applies to static analysis because it becomes important not just to be able to comprehend the code, but also be able to be guaranteed that the code will be optimized so that we can use high levels of abstraction without feeling a guilt that the performance will be coming poorly. And finally, something we've been working on recently is developing the concept of what we're referring to as fixed point oriented programming. Because a lot of the problems I've run into, the way we end up implementing those is a work list. And writing work lists, frankly, as I will show you, is a miserable experience. And I think that's something we can improve on. Okay, so my inspirations for this, sort of at a meta level of where do we learn how to design languages well, well, one of the places I want to look at is way back, Guy Steele's Growing a Language. And I'm sure a lot of you have read this. For those of you who haven't, you absolutely should. I will warn you, the first few paragraphs seem a little bit odd, as you can kind of see here. But once you get into it, you'll understand why he's doing what he's doing. But the main thesis of this is that one of the things that makes the scheme language great is that rather than having a small collection of language experts coming up with what they think the good ideas for the language are, Scheme is a very extensible language, and as a result, gives users the opportunity to extend the language and try what they think is good. And through this process, they can see what others have done, they can borrow ideas, and there's this general evolution that allows us to grow a language and discover what actually works. And this ties in well with concepts from the HCI world. This is another book. It is not about programming languages at all, but it is about how you design objects to be used in the real world by humans. It's a very influential text, and for programming languages people, I think it's a text very much worth reading. The main thesis of this text is that in order to figure out how to design something to be used well, there's basically two things you have to do. Number one is you have to actually build it and use it. And number two is when you are building and using it, when you are using it, you want to pay attention to where are the friction points, where are the pain points. Those are things that you can sit down and try to theorize about, but actually doing it is a much more practical element. And you can see echoes of that in the concept of growing a language, because we can try and build the language and then see where the pain points are and try to evolve it from there. I actually have a demo here today. I'm not sure how much you can see that from the back, but these are two cups that I happened to find in a hotel about 10 years ago. So they're a little bit delicate, and they're the only ones I have, and the only way to demonstrate it is you have to have two of them. So these particular cups, if you actually look at them, there's a lot of design that's going into this. First, there is internal ribbing that provides strength, but it also ensures that when they're placed together, that they do not fully seat. That is intentional and combines with the fact that there's external scalloping that looks decorative, but it also provides an air passageway so that when you stack up these cups, the vacuum effect that you frequently have with stacked cups is much reduced. In addition to that, the scalloping along the bottom is positioned just right, so it tends to lock the cups into a position so the handles line up nicely, and when you have a large stack, it forms a nice little spiral, also very convenient and easy to work with. Finally, the handle on the end naturally forces the hand into a certain grip. And I think the design of this handle was based on the concept that this cup would be holding hot liquids. And so with a normal plastic cup, if I've got a hot liquid in it, it will eventually burn my hands. But the structure of this handle, if you'll notice, the tail is such that my hand is not actually touching it. The way this is structured ends up holding my hand away from the cup. There's a slight gap here in order to make the thumb more natural. There's this lever action happening here, so I don't have the cup here, I just lift it up like that. And also, even the thin structure, which I'm sure was also for reducing the amount of material used, but it increases the thermal resistance so that the handle won't get hot because the passageways are so narrow. So these are the sorts of concepts that you meet within the world of design. And I think that's something that the scheme community is very equipped to experiment and try a lot of these ideas with. Finally, one other inspiration I do want to call out is the works by Tufte. Because within programming languages, it's all about communicating to the human, being able to make the human able to understand, write, develop, debug a piece of code. And all of that comes down to comprehension. So being able to, he's actually written a number of these books. These are his earlier ones, and I think they're more well-known. Being able to look at various pieces of information, and he goes through examples of how people have looked at maps and tried to figure out how to convey quickly and in a way that users can understand well all of the information that needs to be available. In fact, after reading these, I've become a bit of a map collector, and I've actually got a collection up front if you want to take a look at a few different maps, because it is an interesting problem of how do I communicate information. All right. So with all of that said, today I want to propose a few ideas. Two major ideas, and then a smaller collection of other ideas. These deal with the idea of improving the debuggability of languages, in particular designing languages to be debuggable. And the other is first-class continuations as first-class citizens, not just first-class values. All right. As I said before, huge disclaimer here, all of this is speculative. Parts of these slides are going to be wrong. You're going to say, that's not going to work. That's great. Take the ideas, evolve it, do the version that works right. Okay, so it is widely said that debugging is 80% of software development, and if AI is writing some of your code, it's probably a bit more. So that raises an interesting question. If debugging is 80% of development, why aren't we spending 80% of language design focused on debugging? After all, if I'm doing a 10-hour development task, that means I've got 2 hours doing the development, the programming, and 8 hours doing the debugging. Would you rather I double your productivity at debugging, double your productivity at the programming part, or would you rather I double your productivity at the debugging part? Now, there are certain aspects that we see in terms of purity and types that definitely do improve debugging or verification, but frequently it's not really viewed as an explicit goal. And I think that's something that is being overlooked by the programming languages community. Now, when I mentioned this to Will Bird, he did tell me that actually in the game development world, they are very conscious that they want to optimize their debugging process. There's apparently a quote from John Carmack about how if you don't know how to use your debugger well, that's your primary tool. That's what you need to be working with. Sort of like how I would say that if you want to use your editor, your IDE, you want to be able to use that well. But they lift that to the debugging level. Even like when they start up their work for the day, they start by default in the debugger. They don't move to the debugger once they don't program and then move to the debugger once they meet a problem. They start from the debugger. This is secondhand information, so I hope that is accurate. I would go even a step further. Most undergraduate curriculums, I don't think I've ever seen a curriculum that includes debugging as an explicit course. Why aren't we teaching our students this? If this is what's going to matter between spending 1 and 9 hours or spending 2 and 4 hours, this should be a relevant element. Now, sometimes you will have a lecture on debugging tools, but it's usually only one lecture. But it's more important to be able to teach people debugging methodologies. And in fact, I've started to develop one lecture on this. I do not have enough material for an entire course, but I would very much be interested in someone who does have material for an entire course. And if you're interested in what I cover in that lecture, I'd be happy to talk with you about that afterwards. All right, well, that's all great. But what about language design? Can we design languages to be debuggable from the start? Now, I think there's a lot of different directions to go in that way, but I want to propose one example of this to you. So, what are the limitations with existing debuggers? Well, to start with, they're generally considered complex to implement. You know, I think of like, oh, I want to replace the IntelliJ debugger. Oh my goodness, I'm going to have to learn assembly. I'm going to have to deal with interrupts. I'm going to have to learn all of these sorts of things. And that presents a barrier to entry for anyone who wants to like try to experiment with this idea. Maybe I've got one idea that I want to implement, but currently debuggers are viewed at least as complex. However, I don't think they have to be. The second is debuggers are usually an external tool. We see how this can be a barrier to usage. For example, we can see this with the realm of parsing. So in the realm of parsing, you have sort of two categories of parsers. You have the parsers that are an external tool. So these are Yak, or in the Haskell world, Happy. And you also have the parsers that are an internal library. These are things like Haskell's Parsec or like Racket's parse tools. And there's a large divide between these two. When it's an external tool, what happens is developers start to avoid trying to use that. And for good reason, because it's an external tool. I have to go find it, I have to go download it, I have to make sure it works with my current version of the language, I have to integrate it into my build system, I have to learn all of its idiosyncrasies and the command line flags and all of that. Whereas if it's a library, I import, and I can move on. So one of the major limitations with debugging, and in fact encouraging better debugging practices, I think, is that a lot of them are currently external tools. And finally, a lot of them are not extensible, customizable, or programmable. They do have some functionalities, but these are elements that we could improve on. And I hope to demonstrate to you today an example that will improve on all three of these. So in order to do this, I'm going to say, let's try to build the simplest interpreter. And the great thing about interpreters is they can be demoed very quickly. In fact, typically in the very first lecture of my PL course, I try to convince students that they too can write interpreters by live coding one in the first lecture. So we have your standard 6-form scheme interpreter. We have literals in the form of quote, variables, lambdas, applications, conditions, and set bang. And I'm going to say we shouldn't be teaching a 6-form interpreter. We should be teaching a 7-form interpreter. There's only one more form that has to be added, but this one form gives us a lot of power. The way this form operates is that if I call the evaluator, and during the execution of that code, it runs into a debug statement, it is going to exit the evaluator. It is going to go back to a REPL, at which point I can start to inspect things, and then eventually call continue, at which point the code continues executing. As I'm looking around, I can inspect what is the, depending on the interpreter, let's say I'm doing a CESK machine, I should be able to inspect the code, the environment store, and the continuation. This idea of REPLing into the interpreter has been very successful to other applications. Again, in the Haskell world, the Hermit tool allowed people to REPL into the compiler and implement optimizations dynamically and in a live way. And that was able to develop optimizations that we wouldn't have been able to spot before. And you might also notice eval and debug have some very close similarities, both to delimited continuations and perhaps to staged metaprogramming in terms of quote and quasi-quote. I don't know what the exact laws of these are here. That's why I'm proposing this all to you. Okay, so what can we do with debug statement? That's like one thing. What can we do with that? Well, one is if I want to set a breakpoint. Well, what does setting a breakpoint correspond to? It's editing the code. It's inserting a debug statement. Well, what if I want to set a conditional breakpoint? Well, all that means is I'm editing the code to add a condition that tests whether the breakpoint is there. What if I want to set a watch point where there's this dynamic variable, and if this variable ever becomes true, I want to suspend? Well, it gets a little bit interesting there. I'm not sure exactly how it works, but it looks a lot like I'm actually wanting to debug the interpreter itself because I need to include this condition on every step through the interpreter. Then I can start to build up libraries on top of these fundamental ideas. For example, I can implement time-traveling debuggers. How many people here are familiar with the concept of time-traveling debuggers? Okay, about half. So the idea here with a time-traveling debugger is lots of times I'm going through, I'm stepping through, trying to find the point where the bug happens, and I accidentally step one too many. And rather than having to start back at the beginning, it would be nice for me to be able to step backwards. Well, if I have the code, environment, store, and continuation, I can just save those at some point in time, and then later restore them, and I can operate from there. But then once I have that concept, I can implement a form of debugging in the form of bounding and bisecting. So in Git, there's the git bisect command that lets me find the exact commit that introduced a certain bug. Well, if I've got time travel, I can now build a library that says, okay, here's a point where the bug has not happened yet, here's a point at which the bug has happened yet, and we do a binary search. Has the bug happened yet at this point? Okay, the user's going to have to do some inspection to figure out if they think the bug is before or after that point. And it can say yes or no, and then eventually narrow down to the exact point in time at which the bug happens. If this detection of whether the bug has happened can be automated, if I can provide a predicate, now this entire process can be automated. Which also has implications for things like fuzzing, where you could start to explore, does this path lead to the bug, does that path lead to the bug? And so I hope to have convinced you that with this one feature, this debug statement, which should be relatively easy to implement in a typical interpreter, we can expose to the user a way to build their own versions of a debugger, their own capabilities, their libraries, and we can build this ecosystem of tools for debuggable languages. But more broadly than that, even if it isn't this specific technique, I do want to encourage people to consider the debuggability of languages as an important element of that design. Okay, next topic. Continuations as first-class citizens. Currently, continuations are first-class values in that they can be stored in a variable. However, I would contend that currently we are not treating them as first-class citizens. So expressions and values, they can be stored in a variable, they can be inspected, they can be written directly. And this is useful because if I'm wanting to teach someone what expressions are, I can write them down. I can literally show them what an expression is, and I can talk to them about what the variables are that come out and show them those, sorry, not variables, values that come out, and show them what those values are. However, with continuations, yes, they're storable, but there is no way to directly write a continuation. The best you can do is you can write an expression and then grab, during the middle of that expression, grab the continuation that would be implied by that expression. However, it does exist a calculus in which continuations are first-class citizens. They are entirely equal. In fact, there's a formal dual between continuations and expressions. Everything you can do with expressions, you can do with continuations. The two leading examples of this work is The Duality of Computation by Kurian and Erberlin, as well as Call by Value is Dual to Call by Name by Philip Wadler. But there are many other works that have been developed building on this idea. And this calculus, once you develop it, ends up having deep connections to linear logic, sequent calculus, and copatterns. However, the problem with a lot of these systems, in particular these initial papers, is that they're calculi. They're not languages. And calculi, frankly, are very mathematical, and I'm just a poor programmer. And so understanding a calculus is actually kind of hard. I can sit down and stare at it, but I'm always going to be limited unless I can actually try it out and program it. And so what I'm going to suggest today is that just as Lisp and Scheme made lambda calculus accessible to the masses because it provided a way for people to actually experiment with it and try it out and see what it is. And so it's not this weird thing where it's like, oh, okay, so for lambda calculus, you have to do capture, avoidance, substitution, and then you have to understand this equivalences and all this. It's just something we naturally program with and thus develop intuitions with. I'm going to suggest that the same thing should be done for the dual calculi, also known as mu calculi. I do want to highlight there are some efforts in this direction. most saliently, the Duo language by Klaus Ostermann, and Code Scheme, also actually presented, was it yesterday or the day before? I think it was yesterday. And then also mentioned here today by Paul Downen. Can you read that? No. Is there any way we can adjust the contrast? We might have to do that. If I move the mouse, is that? No.
Potentially easy thing is to go to your accessibility settings and invert colors.
We could do that. Could you?
Yes.
You go ahead and try. Yeah, just escape. And then
I stopped the presentation.
Accessibility settings. Yeah, but it's,
but once you start it, and it's like.
It depends on how much black is on the screen is the problem.
The accessibility settings?
Of the display, not the presentation.
Oh, okay.
I guess here? No. Where is it? I guess. Color filter.
Inverted, yeah.
Okay.
Okay.
Okay, try.
All right, we shall see how these colors turn out. See, I want to go back to slideshow, and then from current slide. And then, okay. The colors are going to be, other colors are going to be weird, but most of it's black and white, so hopefully it's okay. Okay. All right, so we were talking about mu calculus. So I want to give you a crash course on mu calculus from the perspective of a programmer. Because if you try to read those mu calculus papers, if you're anything like me, they're a little bit hard to parse. This is going to involve crunching through a lot of code. And I do apologize for that, but hopefully you can start to at least get an orientation of how these things work. Now I'm going to present this from the perspective of a puzzle. There's actually an oddity. If we're operating in a language where we have algebraic data types, there's a weird asymmetry that's happening. So, for example, consider if we have the pair data type, we have the constructor on the left, we have the destructor in the middle. In the pair data type, the constructor forms two sub-expressions. The destructor, it has a scrutiny, it has a couple of variable bindings, and then it has a body. And when we evaluate to this body with the variable substituted by the two forms. Same thing happens for the sum types. We have left and right. We just now have two different branches. Same thing happens for list. This is generalization of all the others. So lambda is a constructor, so it should follow the same pattern, right? No. Lambda, being a constructor, shouldn't have variables in it, but it does. And the thing it evaluates to is the body of the lambda, not the body of the application, which is the destructor. There's something weird going on here. So I want to propose, I'm going to evolve this language into something closer to the dual calculus, which will resolve this oddity. So I'm going to work through this example using the list case. So the first thing I'm going to do is, well, there's already an asymmetry, because eventually the goal of dual calculus is that everything that happens in expression land happens in continuation land and vice versa. There's already an asymmetry in that expressions, they just produce a value. But the constructors, they just produce a value. The destructors, they don't just destruct a value, they say which value they're destructing. Because up here we have case of E. It's not just a destruction. So we're going to erase that. And when we erase that, I'm also going to rename case to mu because that turns out to be the operator that it actually is. However, once I've done that, now I need a way to connect constructors to destructors. And the way to do that is with a command. That command is this angle brackets form, which, by the way, is a very unergonomic notation. But in order to make it easy for you to spot where it is and for consistency, just with past papers, just for the sake of the presentation, I am going to use the angle brackets. And so the idea here is that if I take the E, either of the E's I have here on the left, I take this new C, which you might notice is actually going to end up being a continuation eventually, and I take this C and I plug the two together, then they would evaluate using exactly the same evaluation rule I had before. However, in order to, and I'm not going to justify this, just trust me, this is where it ends up going. In order to make everything fully symmetric, I cannot say that the body of a destructor is an expression because that would be unfair to continuations. So the body of a destructor is actually, a command. It's a pair of two sides. And that gives me the options to be able to choose, am I going to talk in expression terminology or in continuation terminology? Now, what happens as a result of this? Yeah, just double checking. I thought I mixed up these slides. What happens as a result of this is everything I had before, it follows the exact same pattern, except now we have no scrutinies in the destructors, and our bodies are commands instead of terms. And then when I go to mu, something interesting happens. It turns out lambda indeed is a destructor, but it's a destructor of a constructor in the continuation world. Basically what's happening is when I do a call, I'm constructing the call stack in that I'm pairing up the argument A with the continuation K. And then what lambda is doing is it's actually just a destructor of that call stack, and thus gets an argument X, a parameter X, and a parameter K that it then calls off to. It's all CPS. But what this also allows me to do is generalize the notion of functions, because now functions are no longer built in. We have a Turing-complete language without lambda. Instead, it's based on construction and destruction. Lambdas are merely a user-defined data type of one type of constructor. But I could do it with other types of constructors. I've done it with pairs. Well, if I move to tuples, well, I can have multiple arguments, but I can also have multiple continuation arguments, multiple different stacks that I'm returning to. If I look at sums, I basically get case lambda because I have multiple different branches to go to. If I do this for trees, well, I don't know what that produces because I'm not able to program in this language because it's just a calculus right now. Another element that shows up here, because I want to show you what the true mu here is. This is not exactly the standard mu. When you have pattern matching, you frequently have also a nested form for the pattern matching. And if you have a nested form, you also have the degenerate form, where you're not pattern matching a constructor, you're just pattern matching a variable. Well, if you do that for mu, well, what does E mu xq evaluate to? Well, if you follow the evaluation rules, it evaluates the q with x replaced with E. This is let. Okay, well, I can do everything on one side that I can do on the other, so what happens if I swap the two sides? This is let CC. So the interesting thing about this, about mu calculus, is that whereas lambda, I'm making functions my primitive, and data types are constructed in the form of church encodings. In the dual calculus, data is my primitive, and functions are constructed. There are a few tricks that we can have that pop up out of here. For example, in dual calculi, it is very normal to any time I have some expression, let's say there's an integer I'm supposed to produce. Instead, I could perform an eta expansion on mu and say, I don't want to produce that right now. Instead, I'm going to go off and do whatever I want. I'm going to hold on to a continuation, so maybe later I will decide to invoke k, and when I invoke k, that will return the value that you're expecting for E. And so it gives me more flexibility in terms of where I flow with my code. I will mention one major limitation of this system, and if you do attempt to explore this space, this is going to be perhaps the largest hurdle to making it ergonomic, which is that if I have something that in the lambda calculus would just be simply 3 function calls, I get something about like this. Now there's actually two different versions of this. The one above is a little bit simpler, but it ends up reversing the order of F, G, and H. If I want to preserve the order of F, G, and H, I have to do a more complicated construction. Now, that's actually one of the nice things about the mu calculus is I can reorder things in lots of interesting ways, but this is very unergonomic. So this is a place where developing syntactic sugar in order to be able to more easily express these things would be very useful. And the big thing is I can show you some simple examples. But when they developed Scheme, very quickly people learned, started writing code, and they started to notice patterns in the code. And they said, oh, let's abstract this out into the map function. Let's abstract this out into the fold function. We have not gotten to that point yet. In fact, I tell my students that this stuff is so early that simply the act of writing code in this type of language is research, because you will find patterns, and finding those patterns are useful idioms that will help us move forward. Okay, so I hope I've convinced you that it is possible to treat continuations as first-class citizens, but also that this is a place that needs lots of experimentation, needs people to explore the space. Okay, very quickly, because I think I'm basically out of time. Actually, we go to 5:30, right? Yes, okay. So I'm not basically out of time. I'm close to out of time. Very quickly, I want to go over a few other concepts. One is that as currently implemented, macro patterns have a little bit of a problem. If you look at let star, fairly simple implementation, the way it works is by unraveling one layer of let through each expansion. Well, the problem with this is that up here in my let star, I implemented a ... And that ... every time I do a macro expansion is checking the entire list to make sure it's a list of lists of 2 elements. That takes linear time, and I have a linear number of expansions. Let star is quadratic. There are lots of other places where macros could end up having this. Now, the right way to handle this is instead of writing this, what I should write instead is not do that paracheck. In fact, when I first wrote these slides, I thought this was the correct solution, but it turns out there's even a problem with this, because the ... is checking that it's a proper list, namely that it ends with a null. So the correct way to actually handle this is I have to do a full dot. This is a little bit of a problem, because macro developers are being tempted into producing unperformant code if they're not aware. But even worse than that is error messages, because if I do this sort of a system and I introduce a bug, I have the bug there, I'm going to get an error message that says invalid syntax let star bug. Well, as a user, I never wrote let star bug, so why are you blaming me for doing that? Now, for something this small, you can probably spot it, but you can see how in a bigger language this is a bit of a problem. The traditional solution to this is that when you write let star, you have to write 2 versions of the macro. The first version of the macro goes through the entire syntax and checks that the syntax is correct, and then the second version of the macro does the actual expansion process. But what would be far better is if we had context-free grammars for S expressions. And it turns out there's a formalism for exactly that. By the way, this is one of those topics. This is my number 1 topic that is not taught in undergraduates, but I think should, which is tree automata. Just as finite state automata allow us to understand a large number of categories of problems, understanding tree automata, and you only need to read the first chapter of this book, by the way, understanding tree automata is very valuable for doing that as well. You can find this book available online, tata.pdf. You might also have to put tree automata in it so you don't have to remember the entire title, but you can, it's very fantastic work, very nice properties. Now, there are systems like syntax parse that already sort of approach that, but even they do not do everything that is capable with tree automata, because it turns out that there are linear time parsing algorithms for tree automata. So I could have taken my original definition of tree automata, my original definition of let star, and through the parsing algorithms of tree automata, get a linear time algorithm out of it. However, there is still research to be done there because those algorithms were not considering macro hygiene. So once you throw in marks and substitutions, it might mess up some of the caching that those algorithms do with. So there's research to be done there. All right, next topic, readable exceptions. Exceptions are supposed to make error handling easier. And yes, it makes it easier for the programmer, but this is not a message I want to show to the user. Instead, I should be showing a message more like this. Well, how about we add a block statement? And all I ask with the block statement is that you describe what that block of code does. I've done this in my own projects, and the error messages that come out, I was frankly surprised at how nice they are when they come back out. In addition, it actually encouraged me to document my code more, because comments were not simply, because comments now had semantic meaning. Because these basically act as a comment that documents the rest of the code, rather than a comment that doesn't affect the execution. It also provided a focus of what should go here is exactly what to a user would be a user understandable description of this piece of code. As I think has been hinted at a few times today, continuations of macro expansion, or actually after I prepared these slides, it's become more apparent that being able to inspect the context in which a macro is expanding might be useful. For example, in the context of running a parser, sorry, not a parser, a prover, it would be useful to know the context in which you're expanding because that tells you what rules you ought to be applying. By the way, this also relates to the dual calculus again, because I don't know what a macro expander in the dual calculus looks like because continuations are everywhere. So there'll be something interesting there. Finally, programming with graphs. We have constructs for programming with arrays. It's iteration. Okay, I know we don't like that as functional programmers, but it is the appropriate thing for arrays. For trees, we have recursion, but for graphs, we don't necessarily have very good approaches. If you try to write a graph algorithm, it ends up looking like this, despite the fact that there's only 2 lines there that actually matter. I should not have to write all of the other lines. Me and my team are working on developing this. We have the concept of fixed point oriented programming, in which you can write simply the 2 lines that matter. One is about distances adding up together, and the other is the fact of what order you should apply the rules in, and it will generate all of the other code. We refer to this as fixed point oriented programming, and I will note we are still looking for a name for that language, because naming things in computer science is hard. Now, despite the fact that we are working on this and we have our approach, I do want to point out the broader perspective that there seem to be some missing language constructs for graphs. And I would encourage people to think about how would I want to write an algorithm that manipulates graphs. And I will also note that the work that we're doing does have some interactions with the fixed point side and the functional side, but there is some more interaction to happen there. So, in conclusion, I hope to have shared with you, and I hope you do steal. I guess I'm not sharing with you. I hope you will steal these ideas from me. Developing debuggable languages, it's that 80-20 thing. Is it perhaps one of the more important aspects of the design of a language is how debuggable it is. And I think that's something that we've ignored overall. Continuations should be treated as first-class citizens, not just first-class values. And then there's a whole bunch of other things that I'd be happy to talk with you if you have any questions. Thank you.
So thank you for your talk, for your interesting ideas. Regarding the debuggability, what I struggle most with is designing debuggers for declarative languages. So say a debugger of a parser generator or a query language or whatever. Do you have thoughts on how to cover that design space?
I would say that and this is borrowing an idea from Brett Victor, which is the first thing you want to do with a debugger is figure out what are the pictures that you already have in your head of your code, and make your debugger actually show you those pictures. Another element, and this is something I emphasize with my students when I give the lecture on debugging, is the most important part of debugging isn't actually figuring out what's wrong with the code. The code is doing what you told it to. And the problem is that there must be something I'm misunderstanding about my code, because otherwise the code would do what I expect it to. So I want to design a debugger in such a way that it makes it possible for me to figure out where is the divergence between what the code actually does and what I think it does. And so this ties back to that idea of make the debugger visualize what is actually happening. So you have a picture in your head of what happens. Make the debugger generate that same picture in a way that you can start to notice where those two pictures differ.
Okay, but as a language designer, I think the picture that you have in mind is typically influenced by the technology that you use under head. If you building a constraint solver, you know all the unification variables. Your end users typically don't. How would you bridge that gap? And that's a big question, I know.
It is a big question. And I think there might be a lot of different answers. And this is an area where you need a lot of people exploring different ones. And some of them will work and some of them won't. It also is, if you can make your debugger something that your users can develop and extend, then they will naturally build the pictures that they have in their mind. And so being able to try to find the pictures that are, and by users I assume you mean programmers, not language designers, but try to find the pictures that the programmers would have. What is the semantics that they have in their head? But it also works the other direction around, because if you provide a debugger that provides the semantics that you as a language designer have in your head, then when the users load their debugger, you're teaching your users what the correct semantics of the language is. So you can use that as well. These are just some random ideas.
I see. Thank you.
Hi. I was wondering, another question on the debuggable languages idea. There seem to be two large points in the solution space that incorporate ideas that you mentioned. The first being the common Lisp debugger, which is very much built into the language in the same way of the debug statement that you had provided. And the second, especially with that notion of pictures, is the glamorous toolkit, which is based on the Smalltalk environment and also has a built-in debugger notion that allows you to kind of have this picture of here is what this thing is doing, not at a exception and programming language value level, but at a semantic level of here's what I'm thinking about in terms of language design. Would you say that either of those completely or cover a sufficient space of the debuggable language question that you're asking about, or do you think there's like a different dimension that they're not exploring?
So first I have to say I'm not familiar with either of those systems. I've heard legend of them, but somewhere along the line, regardless of the legend, that functionality seems to have been dropped. I would say that there are at least two elements that perhaps could go beyond them. One is to ensure that they are something extensible. It's not just a static artifact. It's something that users can add, experiment, develop higher levels of abstraction on top of the debugger. The other is debuggable languages isn't just developing a debugger. There's many other elements which I did not discuss about what does it take to make a good debuggable language. Part of the reason I didn't discuss those is I don't know what those aspects are. That's something that needs more attention and more exploration. But yes, I think those would probably be very good places to start to look for something that we could mine and build upon.
Great, thank you.
In my opinion, I think what you're saying is to design a debugger, you need to open up the semantics of the language, and I think where you are headed is that I think that leads to reflective languages, and I wonder if you have any comments on that. So reflective language tries to open its semantics to the users so that you can tweak into the semantics. And well, if you change it, then that's quite radical. But if you just observe the semantics, then I think you will have enough information to do various kinds of debugging. So, well, reflective language is not right now very popular, but if you can resurrect that, then I'm very happy to.
Yeah, it sounds like something that would be applicable. I don't have many comments on that other than please go explore, build.
Well, I have a lot of things to tell you.
So the large theme of this talk was ergonomics. I'm kind of curious. Maybe it kind of just went over my head a lot, along with the rest of the mu calculus. What do you find to be in your opinion, going to be the largest ergonomic benefit from the mu calculus?
The largest ergonomic benefit is that currently we're only operating within the land of expressions. Doing anything with continuations is considered weird, unintuitive, hard to visualize. However, everything that exists within expressions also exists within continuations. There's a complete formal dual. As a consequence of this, right now, effectively, we're all breathing with only one lung. We're only programming in the expression land. There is a whole other world out there to be discovered and learned. Concepts such as double-barreled continuations or success and failure continuations. Things like, I'm going to borrow something from the Haskell world, people understand monads, but they don't understand comonads. Hopefully, the idea with a dual calculus is every time you learn one thing, you're actually learning two things. Hopefully, concepts such as comonads, co-induction, these sorts of things, and I don't know, this is just a hypothesis, will suddenly become obvious and easy once that duality is fully exposed. That's one of the things I hope we'll see whether that pays out.
Thank you.
Other questions? Good, because I have a question.
Okay.
Language and thoughts, okay? To debug things, you have to have a language to express them. So the first thing to do is to make people think in terms of the lambda mu tilt calculus. And once they can, when they have been talking about that and thinking about that, then they have the linguistic infrastructure to identify what's going on and to be able to read what's going on. That was a comment, not a question. I'm so sorry. And another one about usability of debuggers, the economics part. I was very impressed by an old colleague at Aarhus University, Susan Bodker. She got awards at SEM not long ago. And the way she worked a lot on debuggers, and she's in human computing interaction. And so what she did was really amazing because she put a camera next to the computer that people were using at the time, and then she recorded what they were doing, and then she studied what they were doing, and then she improved the debugger. So there is the observation aspect that will feed back on the actual design. So listening to the users, seeing how they do that. But that's kind of tied to the language and thought idea. Once people start to think the way you want them to think, well, then they express their thoughts in a language, and that language will be corresponding to the notion of computation that you want. So introducing so there are two aspects: the temporal aspect, how they use it, and then there is the semantic aspect, what they think and how they express that. So I will second the question. How do you think in the lambda mu tilt calculus?
How do I? Okay, that's not the direction I thought you were going. I will comment on your comment before answering the question, which is those user experience surveys are very much in line with at the beginning I mentioned the book about the best way to do learn ergonomics is to actually try it and see what people end up doing. And we don't do that so much in programming languages for multiple reasons, but even just doing that ourselves, releasing a library and letting it out into the wild and saying, hey, I think this is a good thing, and coming back 2 years later and see whether people use it. In itself, even if we're not doing a formal human factors user study, is a form of user study that we can do. And I think that's where a lot of things can be developed. How do I think about the mu calculus? I don't know. I know that I do. I have an intuition, but I will have to spend some more time of thinking about it. Well, okay. Here is, I could spend 10 minutes talking on this. I'm going to try to give the shortest version possible. The way that I think of it is that expressions are things that produce values. Well, actually, let me take a step back. Think about functions. Functions take an argument in and they produce a value back out. Imagine if you'd taken a function and cut them in half. So expressions are that second half. They produce a value, but you never ask the question, yeah, but what was the argument that the expression used to produce that value? It produces the value by combining some variables and some constructors and whatever, but it just produces a value. It doesn't consume a value. In the mu calculus and in continuations, the mu forms just consume a value. They never produce a value. The thing people always ask is like, okay, it takes a value, but then what does it return? The answer is it doesn't. And part of the reason is because the reason it doesn't is it goes off into other covariables. And so I think of expressions as like this hose that's spitting out values, and mu's as this hose that's sucking in values. And so when I do a command, I'm plugging the two together. And the surprising thing is that I no longer have the ends of any hoses left. So that in itself, the commands, they don't return a value, which is perhaps one of the most surprising things people find. It's just that now these variables are connected to those variables. So that's one of the aspects I'm thinking in terms of I'm plugging things together. And they come from some place and they go off to some other place. And I'm grabbing the continuations and other things. I'd have to spend some more time, but that's one of the insights I've had.
So you're thinking in big terms, in big step terms, not in small steps as induced by the calculus.
That's an interesting statement, because in the mu calculus, big step is small step. Because the mu calculus looks a lot like, the underlying calculus looks a lot like a machine already. So even if I try to be big step, I'm actually also small step.
Fair enough. Okay. Now, there's a pre-linguistic aspect to computation, is to just thinking computationally. So I'll give you a very concrete example. I waited my whole life her own life that my daughter asked me how to program. But I fed her during a whole upbringing with logical and algorithmic games. And so when she asked, she was ripe. Now consider that when the kids who are being taught, here is how to use a computer, they have no computational thoughts. And so they are introduced in a language, weird ergonomics to do something that they have no thoughts about. And when you have nothing to think about, well, the language that you're exposed to is kind of empty. So that's why my question about how do you think should like predate how you program is a what and how, language and thought again. So thinking computationally would be the prerequisite, and once you have some thoughts, then a language in which to express them kind of comes naturally.
I would push back on that a little bit because of the stage of development of the community's understanding of the system. It's sort of just like after lambda calculus had come out. Eventually, we're going to figure out what the right way it is to think computationally about this, but we are still having to figure that part out. So we have to present the language. Lots of people are going to try to figure out how to think about it, and hopefully they share those ideas with each other so we can start to develop how do we think about it. I gave you the analogy with hoses, but there might be better ways to think about it. Eventually, once we get this built up, of that this is just a normal part, just as normal as the lambda calculus. You should expect people to understand it just as much as the lambda calculus. At that point, then I think we can start to think more in terms of here's how you do computational thinking, and then add these linguistic aspects. But we are very early days in that regard.
But then about the lambda calculus, I mean, the lambda calculus is really big on substitution. There is no substitution in implementations, they're environments. So that means that all the time that we spend explaining substitutions is for nothing, because it's never reused. And it's only useful if you reuse it. And substitution is never reused. So most of the time we spend on the lambda calculus is wasted.
It was a bootstrap to be able to understand evaluation styles, or using environments, for example.
But then why didn't you have a calculus of explicit substitutions, where there is no substitution, there is the term, and then its bindings? Then people understand closure at the calculus level.
I'm not sure how to answer that one, I think there's a lot of things to be explored here. Is the main message, I think.
Yeah. Thank you. Any other questions?
Could you go back to the slide with the Dijkstra algorithm?
Yes.
Okay. Thank you. Yes. Yeah. What happens? So you said that these are the only two things that need to be replaced. All the other stuff is. What happens if you replace them with something else? What happens if you use a first in, first out queue?
The asymptotic performance isn't what you want.
Yeah, sure, exactly. Yeah, but okay, but you get the wrong result as well, don't you? You don't get the shortest distance.
No, you should still get the same result.
Okay. What happens if you replace it with D1 minus D2? Then you get the wrong result, right?
Yes, you definitely get the wrong result then.
I'm just curious as what class of algorithms come out of that way of looking at things.
Well, it's work queue algorithms. Work queue algorithm, work list algorithms, parsing, static analysis, type checking, most graph algorithms. There's a large number of algorithms. But anytime you're writing a work queue, it'd be much better to write it like this than the other way around. But we're developing languages to be able to do that.
Mm-hmm. Okay.
Last chance. Let's just thank our speaker.
Okay, that concludes this year's Scheme workshop. So thank you all for coming.